AI at IISER Pune. As all of you are aware, the government here is a very big scale event, AI Summit, uh, Delhi, 16th February 20th. And as a run-up to that event, uh, various institutes all over the country are organizing different events which are showcasing what's happening in the exciting world of AI. So when we decided to do this, it turned out that while data scientists of the world are using AI in extremely creative ways, there are not entirely clear to many people what exactly they are doing. And more importantly, who are not in computer science or data science, they are asking the question that, what exactly do I do? I don't want to become a data scientist. What do I do to use AI in the context of my? So we looked around, and of course, we at IISER Pune, many of our own faculty are using AI in many different ways. Some of them are studying AI in many different ways. I thought, okay, let's do something slightly different. Instead of talking about AI per se and what are the latest and greatest things happening in AI, why don't we actually case are not into AI, how AI can be research? And that's what this particular program is about. So as you might have seen, that all our speakers are faculty from IISER Pune. They're going to talk about their work, and the idea is not to take you to the depths of AI. The idea is a glimpse of how AI and methods can be used for other kinds of research. We have a few announcements in. One of our speakers had to drop out, unfortunately, because of ill health. We will have placement for her, and that this is only for people here in the Raman Auditorium. No food, no drinks are allowed inside. Please do not bring those and standing outside will stop you rather forcefully if you try to do that. And also apologize to all those people who tried to cover this event, but because we recap, we cannot include them. That's why we have the YouTube feed going. I hope many of those people have joined us on YouTube. I would also welcome all who are joining us on webinar from different parts of the world. It's a very, very large number of people this, and I hope even larger number end up either seeing it live on YouTube or watching the recordings on as and when up. So that's it from me in the context of. Oh, sorry, I forgot to introduce. My name is Sutirth De. I'm a professor of biology. I head the AI committee today, and you're going to see a lot more of me throughout the day. So at some point, we'll also. So our first day is Dr. Siddhartha Goswami. He joined the data science department at 4, prior to which he was leading an independent group on machine learning in climate science at the University. And currently, Siddharth is working on developing AI models, model weather and climate processes for South Asia, and trying to understand what makes models. So, Siddharth.
Thanks, Sudhir. For nice opportunity for some of the stuff that in our group. So I've called this talk AI for Weather and Climate. It's for AI in Weather and Climate research. And essentially has like short parts. First, I'm just going to show a table. I'm going to basically do an overview of different aspects of weather and climate science that have seen an increase of AI models. Um, After that, the second part of the talk, I'm going to show an overview of some of the things that we are doing in our group, which is mainly focused on weather forecasting. Pick up one example that a student has implemented, and then I does. And in the very end, I'll show you just briefly showcase a few projects which are sort of AI related, but not on weather and climate. But students approached me, try to do it. All right, so let's move on. So here's the brief tour for AI for weather and climate. So basically, this table has the task, which is the problem that they're using AI to solve. Second column will see what problems what kind of data it uses and why it matters, right? And the four problems that I'm going to talk about is nowcasting, midterm or medium range weather forecasting, something called downscaling, which is very important for climate research and also for weather. And the last one is a bit technical, but it's very important to sort of be able to get better climate projections into the stuff that you hear in IP what's going to happen to the world at the end of the century. Something called superparameterization. I'm going to briefly go. All right. So nowcasting, what is nowcasting? Nowcasting is the problem is that you want a very short-term prediction of rainfall and storms on the scale of minutes to hours. Okay, it's very short-term in the sense of the time resolution is very fine. So you have data maybe every few minutes, and you want to forecast also at the scale of every few minutes, and your forecast maybe ends at 6 hours. That's like the horizon. You don't want to forecast beyond that. And it's also spatially very high resolution. So it's when I say high resolution, order of a kilometer. So from here to the airport, it's around 11 kilometers. So you would have 11 nowcasting grid points from here to the airport, right? Which is from weather forecasting point of view, it's very, very high resolution. And you basically have this data from radar. That's why you cannot really do this for the whole globe. So for example, in India, we have certain regions that are covered by ground-based radar. So we have radar stations that can measure some information about how much rain. We have some radar coverage around Delhi, around Bombay, and some specific regions. But the whole of India is not covered by radar. So you can do it in only certain specific places. And you need this because it really helps you in warnings for extremely heavy rains, which are otherwise very hard to predict, and urban flooding, for example, something that can be predicted by nowcasting. The next problem that AI models have been used, medium range weather forecasting, and this is what I really work on, and I'm really interested. And this is what we typically understand as weather forecasting. You look up the weather forecast. What's the weather going to look like at the end of the day, or tomorrow, or the day after? Or if you're planning a trip, let's say a week from now to Delhi, you want to know, okay, what's the weather going to look like in Delhi next week? So that's medium range weather forecasting, and that basically in this, an AI model would be trained on decades of global weather data is available. So we have weather data from roughly 1979, 1980, so it's 40 years of relatively high resolution weather data. So you have weather data every few hours and at a spatial scale of, let's say, 30 kilometers. So you can see the difference between medium range weather forecasting and nowcasting. So for example, Pune would not even, the whole of Pune would be just covered by one grid point, because each grid point in the medium range weather forecasting data grid is separated by 30 kilometers, right? So such a tool will not really allow you to have fine-grained predictions within Pune, for example. But that's not the goal anyway. You want slightly macro-level predictions in medium. And here why it matters is because AI models, once they are trained on the data, right? Once they are trained on the data, then compute the weather forecast. It's like a simple, you feed in the X and the Y comes out, right? It's very fast compared to a physics-based weather forecasting model, where you would have a set of equations. And to compute the forecast, you have to integrate this set of equations over the whole globe or over the region that you're interested in. But it's a large number of ODEs that you have to integrate and then compute the weather forecast, which is much more computationally expensive than just sort of feeding the input conditions to a trained AI model and just spits out the forecast, right? So that's why we found that medium range weather forecasting AI has sort of been able to perform as good as the existing forecast and gives much faster. Then the next problem, which is downscaling, which is relevant for both weather forecasting and climate research, is basically translating coarse weather data, something that is high resolution. So downscaling, for example, if you manage to train a good downscaling model, and typically in this, the AI model will be trained on some low resolution global data and some high resolution regional data sets. So for example, let's say if you have a medium range weather forecasting model that cannot really resolve the different parts of Pune, what you could possibly do is, if you manage to have some high resolution weather data around Pune, let's say from a radar or something like this, you could train an AI model to take in the coarse forecast as X and try to predict the 1 kilometer weather condition as Y. And if you have the training data for that. And if you manage to do that, then you've essentially set up a downscale. And once the model is trained, any future weather forecast issued by the medium range weather forecasting model can be used to sort of predict high resolution weather conditions in Pune as well, based on the downscaling. And this is really relevant for climate research, because climate models, because you again have to integrate these physics equations for hundreds of years to reach at the end of the century or beyond, it's very computationally expensive, right? And for that, most climate models are very coarse. They are even coarser than the weather forecast models. If a weather forecast model is has a resolution of 30 kilometers, the highest resolution climate model probably has a resolution of 50 or 100 kilometers. Right? It's even worse for climate research. And then the question arises, okay, then for a future climate condition, how can we sort of get fine-grained forecasts? So future climate projections have always been rather coarse-grained. And then somebody might come and say, okay, I've trained an AI model that learns to translate this, so we can get the future climate conditions from a coarse climate model and use downscaling to get fine-grained results. And the last one is superparameterization of climate. This again has to do with the computational cost of climate models. So what happens typically is that climate models, as I mentioned, might be at the resolution of 100 kilometers. One grid box inside a climate model might cover the 100 kilometers by 100 kilometers, and the next so on, right? Now, there are many processes that go on within that 100 kilometers which are not resolved, so to speak. Storms might occur and sort of dissipate inside 100 kilometers, releasing a lot of energy inside that 100 kilometer radius, which is basically not resolved by the equations of that 100 kilometer resolution climate set of equations, because the storms might be occurring at, let's say, a resolution of 10 kilometers or 5 kilometers, right? So the 100 kilometer set of equations cannot resolve the storm. But the impact of the storms, I mean, it releases a large amount of energy into the atmosphere. The impact of the storms is though felt at the 100 dynamics that are going on at the 100 kilometer resolution. So we essentially end up in the situation where you have unresolved processes which do impact the dynamics at the coarser scale. And typically then this is taken care of by some kind of expert knowledge, and you say that you parameterize the effect of storms. You parameterize the effect of cloud processes. So you come up with some ad hoc solutions. Okay, if certain conditions are like this, then this particular variable should be assigned this value. Here what AI can do is, AI can take short runs, maybe runs that go for just a year or 2 or 3 years of very high resolution climate models. Not that we don't have the ability to resolve, to model clouds and storms. We do, but it's just that it's very computationally. If you want to create a 5-kilometer model over the whole globe, it's computationally expensive. So instead of running such a model for 100 years, you run it for 3 years or 5 years, take that data, train an AI model to mimic that high resolution model, and then use the output of the AI model to feed into the coarser climate model. Now you basically have, because AI models are fast once trained, right? Now you basically have a model, an AI model, that learns how to mimic cloud processes and storm processes as good as an actual physics-based high-resolution cloud resolving model. And you use that emulator, so to speak, to sort of input the respective dynamics of the storms and the clouds into the coarser model. And that's called superparameterization of climate model. And this has allowed us to sort of, have climate models that can run 100 years at low computational cost without compromising on the sort of resolving the effects of clouds, and right? So that's the last example that I wanted to talk about. So these are four sort of related but yet sort of different aspects of weather and climate research. And there are many more. I mean, every day people are coming up with innovative and novel ways of sort of for weather and climate. But I just wanted to give you a brief overview of, and if you're interested, I've got some backup slides with pictures and so on. But in the interest of time, I'm not going to. Right, so what I am interested in is mainly medium range weather forecast, midterm weather forecast. So I'm just going to briefly just talk about this. And here, for example, we have a forecast that was issued 12 hours before for longitudinal winds, so like winds that go along the longitudes, at 850, at something which is like, just a kilometer above the surface of the Earth, for 1st January 2023, a sample taken from 1st January 2023 at midnight. One of these forecasts is from an AI model, and the other is from a traditional physics-based model which has been in development for like 40 odd years. Which one do you think is from AI? The left one or the right one? So so show of hands, who thinks AI model is the one on the left? Show of hands. Okay, one, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Show of hands, who thinks the right one is the one that's coming from the AI? Okay, this is much bigger, like this is probably 20, 25 or something. Right, and this is really not a trick question. The left one is from physics and the right one is from the AI model, so the second group, you got it right. But I mean, it's safe to say probably, I mean, you would agree with it, that's like a coin toss, basically. I mean, if I were to ask you, why did you choose this? Probably would not be able to. The point here is that, like, these are really extremely, they look very similar. And in fact, I've not showed like, scorecards and leaderboards, because that would take much longer to explain. But so the first AI medium range weather forecasting model was from NVIDIA that came out in, I think, 2021 or 22 something, like 3 to 4 years ago. And that as an archive preprint. And the first peer-reviewed published AI paper probably came out in late 2022. And in like the span of 3 to 4 years, they've outperformed the physics-based model in several, like they're almost as good as, and in some cases, for some variables, they actually do better than the physics-based. And you have to understand that the physics-based models have been in development from like, the like the modern version of what we know as weather forecasting probably had its roots in somewhere in the 1980s, right? So on one hand, you have 40 years of development for the physics-based models, and like compared to 4 years of developments of the AI. So the pace of development is extremely amazing, and the second is the quality is also like really. It's the first time I saw this. It was quite ground shaking. All right, so this is just to give you a feel of like how AI models can really be almost as good as physics-based approach. There are issues with interpretability and explainability and so on, but as of now, they work and we can use them. And this, in fact, both these models are from the European Center for Medium-Range Weather Forecasting, which is one of the most leading agencies of weather forecasting in the world, highly respected. And the physics model is also from them, and the AI model is also from them. They call it AIFS, so AI Forecasting System. Right, so let's move on to what we've been doing in our group. And again, the main focus in our group is on weather forecasting. So here's basically a list of projects that are going on in our group. So we basically are implementing some of the publicly released high-performing AI weather models. We are re-implementing in-house at IISER. And of course, we are not implementing the full-blown model because that would, like at the developmental stage, you don't want to consume so much resource. We are sort of implementing mini versions of that. So Vishnu has been implementing something called ForecastNet, which was originally released by NVIDIA, and he's doing it at 1.5 degree resolution. Then we have Arpit, Ayush, Ashik, Bharat. They are implementing like Pangu from Huawei, Fuxi, which is from Fudan University, GraphCast, which is from DeepMind, Healbit, which is from another small startup called Xcarta. And these are at coarser resolutions because we're just trying things out right now at 5.6. So 5.6 degrees would be like really coarse. You only have, over the whole globe, you have like 64 pixels on the longitude and 32 pixels latitude, something like 200 kilometers or so. So it's rather coarse, but just to give you, again, a feeling for what we have on our hands, let's just look into this project from Arpit, who's implemented a mini version of Pangu weather, which is based on a vision transformer. Right? So this is how the structure, this is kind of copied from the paper of Pangu weather, where the problem is something like this. So you have really a lot of high dimensional input data. So on the left here, we have the input data. You have upper air variables, so temperature, winds, humidity, pressure from the surface to the atmosphere, and then you have some surface variables as well, which are like surface pressure, surface temperature. These are not these are defined only at the surface. And as you typically do with a vision transformer, you would sort of like create patches out of them. And here, because it's a 3D problem, the patches are 3D, and then they are sort of merged and fed into this transformer model. And then there's an encoder and a decoder, and finally you spit out the final forecast on the right, which is essentially looks like the same. It has the same structure as the input, but it's just that the input is the state of the atmosphere at time t on the left, and then this state goes inside the transformer and then spits out the output, which is the state of the atmosphere at time t+1, right? And then you take that and then feed it back to the model, and then it gives you the state of the atmosphere at t+2. And then you do it again, and you get the state of the atmosphere at t+3, and you keep on doing this. And that's how you use an AI model to get a weather forecast. This is just for completion's sake, we have data, we have training period from 1959 to 2017, a validation period, and so on. Grid size I've already talked about. The data is sampled every 6 hours, and the variables I've already sort of feel for that. And this is what the results from Arpit's model looks like. So on the left, you have the ground truth, and for some randomly selected time sample in the test data set, I don't remember the exact date. On the right, you have the predictions at just one time step ahead, which is 6 hours later, right? The top row is for winds which are going in a latitudinal direction, and the bottom row is winds which are going at the longitudinal direction at 10-meter height, which is something like at the second floor of a residential. And again, you see, this is the target that we are trying to model, and this is the prediction that you get, predicted 6 hours before from one time step before. And it's, again, it looks very convincing that this is working. However, I mean, there's still a long way to go, because there is this one particular evaluation metric called ACC. It's essentially a kind of a pattern correlation between, so if you do a pattern correlation between this map on the right and the map here on the left, then that is something like, that gives you a value which the ACC in some sense. So it's a pattern correlation of predicted deviations versus actual deviation. And the general consensus in the forecasting community is that if this value is above 0.5, then the forecast is a usable point. So here you have forecast lead time, which is like how much time ahead you forecast the conditions in days. And we see that around after 2 days, the ACC falls below 0.5 for Arpit's model, which means that after 2 days, Arpit's model is useless, basically, for forecast. So we do have a long way to go. The actual Pangu weather ACC goes down below 0.5 after like 15 days or right? So we are nowhere near that, but we are making small steps. And then, all right. So the road ahead would be, so, we want to increase the data resolution to 1.5 degrees, which is what they're working on in this semester. Increase the variable set, of course, improve ACC, and and then the final thing is we want why we are doing this, why we are re-implementing sort of these models. On one hand, it's really cool, and you really get to learn a lot. But the other hand, if we have them in-house, right, we can actually use them as a baseline to sort of test and develop our own model that can outperform these models, which is ultimately the goal for our group. Right, so that's basically what's been going on in our group. Let's now, just before we end, I'm almost out of time, I'll just briefly give you an overview of 4 projects, 1 slide each, of non-weather, but still AI stuff being done in our group. Okay, the first one is Utpal. He basically approached me and said that he wants some kind of language modeling. So last semester, Utpal managed to get a first results of a compact Hindi language model. So it's a small language model. So all of you are familiar with large language models, right? But there are also something called small language models, which can actually be used, which are increasingly becoming popular because they are easy to deploy. They can be deployed in cases where the internet connectivity is not that great, where computational resources are not that great, and so on, right? And that's the training curve of Utpal's models on the right. And here's a sample of his. So if you give the prompt like Bharat mein barish kab hogi, then the model says it's not really great, but it still does something close to what you would like. Is the topic related? So इसकी संभावना कम ही है. यहाँ का मौसम शुष्क रहता है. यहाँ की नमी से लोग परेशान रहते हैं. मौसम शुष्क रहने के कारण यहाँ का अधिकतम तापमान 35 डिग्री तक पहुँच रहा है, and so on. Like it spits out something. But this is just the first step, the first result. Like we have a model that takes a Hindi prompt and gives in Hindi some text as a result, and now we basically he's working on fine-tuning this model. And this is also the same case for LLMs, by the way. Like, without fine-tuning, an LLM also spits out garbage like this. Okay, so that's Utpal's project. And then we have Dinesh, who's a mathematician essentially, and he is working on something called adversarial robustness. And Dinesh's work typically involves, assuming stuff with a lot of mathematical notation and then proving stuff and so on. And I just try to take a step back and just guide him and as best as I can. But this is also pretty cool because he's working on something called adversarial robustness. Without really getting into details, so adversarial robustness deals with the fact that AI models are susceptible to some targeted attacks where, like, you can take the input of an AI model and just add a little bit of targeted noise, a very well-crafted noise, which is imperceptible to a human. Let's say an image of a cat, you add some noise that our eyes cannot detect, but that image, when you feed into a well-trained AI model, the AI model starts to spit out garbage. It says that the cat is a hippo or something like that, right? Like it does not recognize it, that it's a cat anymore. So that's called adversarial attacks, and that's related to adversarial robustness. And then we have Prakhar, who's doing something called, like, he's basically using an image segmentation model that Meta released. It's called Segment Anything Model, SAM, and he's added some adapter network to the front of SAM and to the side of SAM so that we can use SAM to basically classify something called atmospheric rivers. So these very thin tendrils of water in the atmosphere. So typically rainfall happens in large circular blobs, but sometimes rainfall also tends to happen in these thin tendrils, and they dump a lot of water. And it's an interesting problem to sort of try and quantify. And then we have Kostov, who's doing a master's thesis on the Arabia butterfly, basically trying to understand how climate can drive the morphology of the forewings and the hindwings of the butterfly. And he's also using the segment anything model, but he's fine-tuned the model to sort of be able to take an original image like the one that you see on the left and give you a mask of only the wing. So if you take SAM, because SAM has been trained by Meta on like just a general popular image database, it's not a research database. SAM does not know so much about research. If you just take SAM naively and ask it to sort of like, segment out only the wings of the butterfly, it does not do a very good job. So Kostov had to sort of like, create a label data set on its own and sort of fine-tune this. Right, and so that's basically it for my talk, AI for weather and climate, and some other stuff attached to it.
Thanks, Siddharth. We are slightly short of time. We'll take maybe 1 or 2 questions. So people who have questions, please raise your hand up. People who, somebody will come to you with the mic. And people who are watching this on Zoom webinar, you can type your question, the Q&A thing. Obviously, we won't be able to take all the questions, but if we have time, we are going to take 1 or 2 questions from the webinar people as well. So yeah, raise hands. That one. Identify yourself, please.
Good morning, sir. I'm Oishik. I had a question related to nowcasting. So presently, you said that nowcasting can only predict weather and climate at maybe a few minutes or a few hours before. So are we looking at a system? Is it possible to create a system where nowcasting can predict flash floods and heavy rains even before that? So for example, taking midterm weather forecasting and use some downscaling process to predict micro level weather. Is it possible to do that?
Principle, yes, and some people are trying that, but it's a difficult problem.
Yeah. Anybody else? Yeah, Professor Gadakar there. First row.
Thank you. Can you give layman some idea when this happened and what kind of difference it made for a user like me? Can I perceive that?
Some idea because that explain the transition. Okay.
And when did it?
I think the first model which tested out whether an AI model can sort of predict the weather or not was a very a proof of concept small model that came out in I think 2019 or so this is concomitant with this general AI boom that has happened because of like easy access to and sort of overall like language models becoming popular. So at some point some sort of asked the question, okay, can we use a CNN, a convolutional neural network, which is very popular even now, sort of predict the weather, because a lot of success was being seen in computer vision, which all vision related tasks. And if you think about the weather maps, they are also like a 2D image sort of like. So you can maybe borrow the ideas from computer vision and apply that. People tried that and they saw that there was some promise to it. Although back in 2019, somebody from the Met Office, a very senior person, famously said that like we have to wait for a few decades to see the AI models to sort of outperform the physics models. But then that was not the case. Without that. And all the companies sort of jumped in, right? And then they have a lot of resources.
What I see.
No, what you see on your phone is most likely not AI. What you see. So it's one thing to have a weather model in the research space, and it's completely another thing to operationalize it. Because to operationalize it, you also need to get the initial state of the atmosphere. That again is a complicated process. So ACMWF, the European Center, they have taken first steps in this. So they have an operationalized AI model. That was the one that I showed the picture from, AIFS. But I'm not really sure if that has percolated to the level of apps yet.
Sorry, people on Zoom, we couldn't take your questions. We have a slight time issue. So our next speaker is Professor Arnab Mukherjee. Professor Mukherjee joined IISER Pune in 2009 as an assistant professor and currently the full professor uh, the Department of Chemistry. He works in molecular recognition, protein folding, and related areas. And recently, he has started working on machine learning and deep learning approaches to biophysical problems such as drug design, conformation prediction, and so on. And coming out of lots of experience of personal chats with Professor Mukherjee, I can tell you he is probably the biggest enthusiast of AI on this campus. Okay? So yeah, Arnab.
Okay, so thanks, Udit. And he has organized this in a very, very short time, just to showcase the, the effort that IISER Pune faculty are doing in this particular area of AI. As you know, that AI has really, has infiltrated in, all different disciplines, science, arts, and everything. And even from, from the point of view of chemistry faculty, I can show you that where we can use AI, at least partly, AI can be used in chemistry, multiple different areas, but I will talk about one of them. So what I'm going to talk about today is essentially how to design a protein mutation using AI. It's a biological problem. Often we need protein mutations. Okay, before that, this is the campus. All of you who are from outside and directly came to the auditorium and didn't see the campus, this is just the front area. It's a beautiful campus. You can see that. So, so what happens is that we often protein mutates. In the natural process of evolution, protein gets mutated, and after that, if it is selected, it's good. Then it is selected. Otherwise, it is rejected, and that's how naturally it happens. However, there are also efforts on directed mutation. For example, you know that the structure of a protein depends on the sequence of. Now, if you change the amino acid in that protein sequence, then the structure will be different and its function also different. Now, what happens is that, let's say, if I want to target a particular protein like this one, and proteins are also enzymes. You know that protein does a lot of enzymatic functions. Now, if I want a particular protein to do certain kind of a function, then I need at least get to that particular structure here. Now, if I take a different protein and do a mutation in such a way that it comes to that particular structure, then it might also do that function. So it is actually, you can say it's a directed evolution in which we are directing the system to go towards a particular structure and function. It's a hard problem, and you have to try randomly multiple mutations with a lot of domain knowledge, the knowledge of the field. One can probably do that, and that's what Francis Arnold is working on and published the paper on directed evolution of silicon carbon bond breaking enzyme. Now we want to do the similar thing, not as complex as this, using AI, but I'll talk about that later on. So what is our problem is much more simpler than that. Left hand side there is a protein where the magenta color is showing the helix. And we want to do some mutation in that helix such that the final structure helix will be. As very simple problem, that's what we want to do. Now, although it sounds simple, it may not be in practice, because when you do experiment, when you want to try that, how do you do that? So you will take a sequence and you will have to synthesize to what kind of protein it is, and typically you characterize the structure of the protein using spectroscopic method. CD spectra is one method by which you can see whether the protein contains helix or not. And then you will get the helical content. After that, you will have to do some mutations in that helix in order to see whether the helix is broken or not, because that is the objective. Now, this process is pretty long if you see, because if the amino acid, there are many amino acids, for example, then each can do a single mutation, you can do double mutation, triple mutations, and in different positions you have to do mutations. And you know that there are 20 amino acids. So the total number of mutations that you have to try is quite a lot. So if I write down, so for example, for a sequence of length n, I can mutate from number 1 to n. And if I have to do p number of mutations, then I can choose ncp. So I have to choose from n, and then that particular amino acids I can mutate to any other 19 amino acids. So 19 to the power p. So it's a large number. That's all I wanted to say. Mass is not important, but the important is it's large number. Now, how do we replace that using AI? So we take the sequence. Now comes the most important part. This work could not have been done, 3-4 years back. Is because it requires direct structural elucidation, or basically finding the structure of a particular sequence. And it was not possible before. Only recently, using AlphaFold and then followed by that ESM fold, we are able to predict the structure of the protein. And ESM fold is more important because the thing is that AlphaFold does sequence matching to do the structure. So if I change one amino acid, AlphaFold will pretty much give the same structure. However, ESM fold is something where single sequence to single structure is predicted, and using ESM fold will predict the structure. And then, of course, we will characterize, not using CD spectroscopy as an experiment, but using some algorithm. Here we are using something called PC algorithm that kind of tells you from phi psi angle itself you will know whether there is helix or not and how much helical content is there. And then instead of learning, see, earlier we were learning, while doing experiment we were learning that okay, which mutation is taking the helix. Now that learning has changed to machine learning. So machine learning, of course, is a part of AI. Okay. So, and what the typical machine learning that we are going to do, that I'll talk about here. So this process in computer, reasonable size computer, takes 1 second per peptide. So you can see that I can try a lot of mutations in this, and I will be able to understand. Now all of you who are not initiated into understanding how AI works and all the gimmick of AI and all this hype and things around it, it is essentially very simply a function fitting. Many of you probably have fitted a line, lot of data points, right? And that is machine learning. What machine gave you for fitting a line? Values. One is the slope, another is intercept. If you know these two values, you can draw the line. And that came from your fitting of the line to the data points. Now, instead of line, you can fit a curve, you can fit a polynomial. Instead of one dimension, you can use multiple dimension, and things will become complex. But even then, essentially, it is nothing but fitting a function, a complex function. In machine learning, we are not even beforehand itself telling the function. We are, giving it a very big complex function and asking the machine to fit that function and get the parameter. So f is the function and theta are the parameter in general. Now, there are different types of machine learning there. I talked about line fitting, which is supervised learning, knowing the data, you fit the line. There is unsupervised, which means we don't know anything about the points, but we know they are different. That is unsupervised. We can cluster them. There is semi-supervised learning, and there is something called reinforcement learning. It's slightly different. And I'll talk about a little bit more about that. In reinforcement learning, essentially we don't fit XY data point, but what we do is that we take an action in a space. So let me show you the game first. Many of you probably have played game where there is a ball that is supposed to hit the bricks and break it. Now if the ball comes and hit the ground, then you lose the game. So essentially you have to move the bar such a way that the ball hits the bar and goes back. Then we win the game. Now this game that you see, it is being played by reinforcement learning algorithm, and pretty much you can write it in a 1 day itself. If you are interested, let's go to the blog of Andrew Karpathy. He has pretty much written that in his blog, how to get this thing done. What you need here is a lot of images, snapshots of this game, and you have to program it. So you see, the interesting point is that even when the ball is far away from the bar, the bar, it is being able to predict that which side the bar has to go. So it is being able to predict the future thing based on the current context. And that is what the reinforcement learning essentially does and learn. I'll give you more example. So what it does essentially is that in any environment, you have to take the program, the agent is essentially the program. The program takes an action in environment, action is AT, and taking that action, it goes to a new state. And in the new state, if the state is favorable, you will get a reward. If it is not get a reward. For example, reinforcement learning is inborn in us. When a child learns to walk, if the child, after taking one step, it falls down, the child knows that, what not to do. But if it can go, then, the child will, do that same thing, right? So essentially, we learn by experience. So this is something you can say that learning by experience. I'll give you more examples which probably will be clear. So here is a game of chess. Now you know that when the AI boom happened, these programs actually broke the record of the chess player and then the Go player, which is essentially considered to be even tougher game than chess. And the world champion in Go game was defeated by the AI model, essentially using reinforcement learning. So what it does is that this game of chess, this is a state. At any point, the state of the board is the pieces that are there in places, like take a snapshot. Then someone makes a move, and that is the action that you take. That moving that one of the piece leads to a new state, and if that new state eventually leads you winning the game, you will get a positive reward for that action. Now you may take a wrong move, a bad move, and still you may win. Still you will get a positive reward. But statistically speaking, if you take a wrong move, then statistically you will not win. Statistically meaning, if you take a wrong move 10 times, then only maybe 1 time you can win, but 9 times you will lose. So on an average, whether a move is good or not for a given state is what reinforcement learning learns, which means you have to play the game again and again, again and again. And with that, you will encounter all sorts of different states, and for each state, you will know what is the action that you have to take. For example, right now for me, this particular state, what is my next best action, such that at the end of the game or end of the show or end of the thing, I get a positive reward. So, self-driving car is another example. There, the state is the car on a road with all the obstacles and everything, and action is essentially turning the wheel. Now, if you turn it too much, you will meet with an accident, and that is a negative reward. But if it doesn't happen, if you go and move without any problem, then it is a positive reward. So a lot of us played a game. You have there is no stick, right? So remember a game of stick that you used to play on a finger. We look at the top and move it. That is essentially the program called cart hole, and that is one of the first implementation of reinforcement learning people use when they start learning reinforcement learning. So last one is very lucrative, that is the stock market. For example, in any given state, you can have 3 things: either buy the stock or sell the stocks or hold the stock. Now, by doing that today, if it gives you a reward or a lot of return 10 days later, then this decision that you have taken, the action that you have taken will be positively reinforced, and essentially you will learn what to do for any given point of time. So you see that reinforcement learning essentially is there in different walks of our life, and now I'm going to talk to you about how to use that in our problem. This is a little bit more detail of reinforcement learning. So here is a very simple game. There is a rat. Now there is a cat on one side, cheese on the other side. Now obviously we know that the rat has to go towards the cheese. Then it will get positive reward. If it goes towards the cat, it will get negative reward. However, there is no reward in between. So how does it know that which direction to go? So it will try right, left, everything, but eventually when it comes to the terminal side of reward 100, it knows that that is the side to go. And if it comes to the other side, it will get minus 200, whatever number it is, but it's a negative reward. It knows that not to come that side. So by doing that again and again, it will get an overall reward. So mathematically it is written G as the return of reward at time t plus 1, t plus 2 and all that. And you see there is some small gamma is there that actually tells you that you have to do it faster. See, I can go to the cheese, but after a lot of spending time in the middle, I can go to the cheese, or I can directly go. Directly going is of course favorable. If you go directly, you'll go in 3 steps. If you go like 100 steps, then obviously your G will be lower. So G overall is called discounted reward. Whatever it is, the point being is that finally if you reach your terminal state and if that is favorable, then you will get a positive reward. And that will reinforce all your previous actions, and you learn what to do for a given state. Okay, so mathematically, who likes mathematics? So E is the expectation. Expectation is on average. Tau is the trajectory, and G is your overall return of the trajectory. So what does trajectory mean? From your given state till the end, that is your trajectory, because it's time step, right? Trajectory essentially is combination of several time steps. So on the overall trajectory, whatever G you got, that you have to do it multiple times, and on an average, if that gives you high positive value, then you know that that is a better one. And essentially, pi is called the policy. So policy essentially tells you that what action I need to take in a particular given state. That is my policy. And that policy you are going to learn for maximizing your return. For example, when you fit a line, you minimize the error between your line and the points and square it. Of course, square error, we call it mean square error. We minimize that, right? Which means that we maximize negative of that. Here we are maximizing the reward that we want to get, and the reward comes at the end of an episode. Episode meaning when you start till when you reach your terminal state, either the cat side or the cheese side. We can also decide that I will only go for 10 steps, and then I will reach a terminal state. Okay, that is called one episode. Now with this framework in place, this is the entire mathematical part, but I will skip over it, and I'll just tell you is that what is a neural network? A neural network essentially gives you a framework to write that function. It is complicated function, but it is function nonetheless. Now, given the state is input to this neural network, and output is your action. It will tell you, let's say if you have 3 actions, buy, hold, or sell, then it will give you buy, hold, and sell with different probabilities. Choose the one with highest probability, or other way, and you take that action. So essentially, your neural network is learning the parameters theta that goes into your function pi, and pi is the policy. Okay, now how do we do that in our problem of mutation? So I take a sequence. Now in computer everything is data, whatever it is, whether it's a car or a chessboard or whatever, ultimately it will be number. So we convert the sequence to numbers or vectors. Then our action is mutation, which means we'll replace that amino acid by another amino acid. Our output is a new sequence. That D is shown there. It's a new sequence. That is also written is in terms of numbers, vectors. Now action is taken. Now I have to see whether the reward is there or not. So we say that I'll give you positive 10 reward if you break the helix. I'll give you minus 25 if you cannot break the helix at all. And every step that you take and cannot break the helix, I'll give you small negative reward. So this is how this has been input into the program. And how do we model that? You see that there is a sequence. Sequence will convert to a vector. That state is a vector. Neural network takes an action. After action, it mutate it, and reinforcement line. So this is pictorially it is shown like that. Yeah, you can see that. Now this is the protein and this is the helix. I already shown you. Now what we do is that we give the entire protein also as a vector, and this sequence is also as a vector, and then we concatenate them, because the program has to learn, right, that which one has to mutate. So That's how this is, together it is given, and then this whole state is input to the neural network, and output is our actions. How many actions are there? If I have 15 amino acids, each amino acid has 20 possibilities. So 15 into 20 is 300. 300 total actions will be there. Time. So now we have actions. We'll use that action to mutate it, and then we will get result. Now this is the result. So I'm skipping the part in between. Now how difficult it is, you might think that is it very difficult to do? Actually not, because earlier, see, when people, I would say that when they first learn to write programs, they had to write themselves, right? Learn programming and all. Nowadays, you can write programs in ChatGPT itself, although you have to know whether it's a right program. Similarly, reinforcement learning, are familiar with Hugging Face model and all that? One can download from that, one can get that model. So the model that we use is called proximal policy optimization. It is something related to policy gradient method, where we are actually, gradient essentially tells you to go to the direction of minimizing something. So policy gradient essentially tells you that instead of taking a random policy, the policy has to optimize in such a way that the maximum reward can come. So whatever we know, something called objective function, that either we have to maximize or minimize. How to do that? That protocol is also there. Steepest descent is one of the easy one. There are many other methods that there. Essentially, we are doing everything in the framework of a function, then optimizing that function. And whatever comes out is our optimized parameters, theta, for the function, and then we can use that. So we use that. We got our optimized parameters by doing that, and we use that for some protein called frataxin. The wild type, the original one, is shown on the bottom right corner. And the magenta color is the helix that we want to break. Input has been given. And you see, we get all the models. All these AI models are probabilistic in nature. They don't give you definitely one number. Everything is probabilistic. So essentially, you will get lots of different answers, not just one. And you can pick the one that is best suited. So we got all these possibilities. But you see, they are very specific mutations. For example, I will just talk about one. So this one, you may not be able to read it because it is too small. It says that 186 residue change from leucine to aspartic acid. Number 188 change from alanine to glycine. Number 190 change from leucine to glycine, and number 192 lysine to aspartic acid. So this is 4 mutation wala system, but there are 3 mutations system is also there. So now you don't have to even decide how many mutations and where and to what. These are the 3 possibilities. It tells you that do 4 mutations, do in these places, and do from this to this. It has learned, and it has learned in general, which means that it is protein agnostic. I can take any protein that I like. And we have taken frataxin, and we have taken another protein L. And again, the wild type you see on the bottom corner. By the way, all the predictions are through ESM fold. And ESM fold is not 100% accurate. It is only 74 to 80% accurate, which means that I am taking ESM fold structure to be 100% accurate, and that's how the model is built, which means that my model may be wrong also, because if the ESM prediction is wrong, okay? Because it's not experiment. If you did the experiment and then use that as reinforcement learning, that would be much better. But that is not practically possible. Protein L, and we have done for many other proteins. So once the model is ready, you can deploy it anywhere. Once you learn, self-driving car, you don't do it from car to car, right? For one car, you have done, it will work for other cars also. So now, only problem with all these AI models is that, does it hallucinate or not? 5 minutes? 2 minutes? Okay. Does it hallucinate or not? Hallucination is something that it feels like I'm seeing it. That also comes from, if we start doing many things like that, we also will tend to hallucinate something. So AI programs also often tend to hallucinate. So you have to always cross-check that is it hallucinating or not. The way to cross-check it is using our standard method of computational chemistry and biology, where we can understand whether a particular sequence will fold to a particular structure or not using something called free energetic calculation. I will skip the technical detail of it to tell you that free energy calculation is complicated. We cannot do by normal MD simulation. We have to do some sophisticated techniques like metadynamics. I'll go to skip all of that. Just to show you the result is, look at the blue color. Blue color is my wild type protein, where the free energy minima, you know that for most stable state, it will go to the free energy minima, right? So free energy minima corresponds to minus 40 degree psi angle. Now psi angle for a helix is minus 40. That we know. And what we see is that for wild type, it is at minus 40, which means it is good, which means my wild type should be helix, and it is helix. But look at the mutant. After mutation, the free energy minima changed to plus 50, which means it is no longer helix. It has broken. So if it has to be in helix at minus 50, then the free energy will be very high, which means it is not stable. So by mutation, the calculation shows mutations, the structure naturally change to a different structure. Okay? Because we take the structure that is at the free energy minima. Same thing happens for the other protein also. The blue one is a wild type where minus 40, there are two minima here, surprisingly, minus 40 and another one, but at least minus 40 is there. But red one goes to the other one. Okay, so and we can try that for multiple proteins. This is just to show kind of an idea that that it is working. However, without experimental evidence, we cannot say for sure that it will always work. So that part is not done because I am a computational chemist. But in future, of course, we will have to try it out and see whether it is working or not for a complex protein. And you can do many other problems with this. Let's say you want to mutate it such that it becomes beta sheet, or you want to do something such that it forms a particular structure that you like, a cavity where a protein binds, where the molecule binds. So all those things are in the possibilities, right? Only thing is that one has to just keep trying it, of course, with some idea, some knowledge, some thinking, and all those things. Okay, so with that, I just kind of conclude that we use reinforcement learning to do protein mutations such that it serves an objective function like breaking a helix. And we tested that onto proteins, and we noticed some interesting thing also, that aspartic acid is breaking the helix, which was not known that much in the literature. And we know that alanine favors helix, glycine breaks helix, proline breaks helix. We removed proline because proline will break helix anyway. So, but aspartic acid, coming out to be something there for breaking the helix, at least in this particular case, is something interesting. So we learn all those other things also. So my student, 5th year student Prathit, worked on it actually. It was his 5th year master's project. Right now he's just waiting to join for a PhD in UC Irvine. And we have a big computer, and we call it Param Brahma supercomputer, that was extremely helpful for us to do this calculation. With that, I thank again all of you.
Thank you, Arnab. Yeah. Do we have questions here from the audience? That video with it. Yeah. People in Zoom, if you have anything, feel free to write. Yes.
Hi, sir. Actually, in supervised learning, we train the model by input data as we, but for as reinforcement learning, we do give them data for training, or they just learn by themselves by doing it multiple times?
They learn by themselves. So one thing, at the final outcome, you have to know what you want. And if it reaches that outcome, then it will get a positive reward. But they have to do it by themselves. The actions will be taken by the program itself in a given state. So yeah, so that is essential, that it takes some kind of an action.
Okay. Anything else? Anything? Okay. One over there. That one. There.
Here.
That hand. Yeah.
Good morning, sir. Sir, what determines the positive and negative rewards in reinforcement learning? So how much positive reward I give?
That is a very good point. So that is, you can say in machine learning language, hyperparameter. That you have to change yourself. that what is giving the best output. There is no standard protocol there for doing that. Obviously, if you don't want something, you will give much more negative reward than something that, and you don't want things to, you have to do it trial and error on that in order to really see what is working and what is not working. Hyperparameter. Yeah.
Just 1 second, yeah. Give the mic over there.
Thanks for the talk, Professor. I think it was one of the most lucid explanations of reinforcement learning. Thank you so much.
Thank you.
I just wanted to go back to the beginning where you said that one of the objectives of this was also to create a model of your own at some stage, like AlphaFold, ESMFold. When do you think that will happen and what will be required for that?
So ESMFold and AlphaFold is something that predicts the structure given the sequence. And of course, they use billion parameters and all that, and that requires a huge computational time. So that was not my actual objective. So I was using that to train my reinforcement learning model, give us the prediction of mutation for a particular structure. So what I want essentially is to try it on another situation where I want to mutate and it will give a helix of, helix will be broken to a beta sheet. We are working on that. Or it will give me a very different type of structure that suits a particular function. So let's say a cavity. So those are the things that people are already trying to do in order to go towards engineering a particular protein for a given function. And for that, we don't need another ESM fold because we already have too many of them right now, omega fold and many others. What we need is that even simple application of that may not work. We think more intuitive how to model them. So that work is still going on.
We'll take that one last question and we'll end with that one. Yeah, the mic is coming to you.
Good morning, sir. My question is that, as like in the machine learning, we divide the database into the training set and tests.
Correct.
The reinforcement learning, do we divide database like?
No. So here, so training, test, and so that is for supervised learning. You do that training and testing. But here, you are generating the new data all the time, right? So when you take an action, it gives you a new data already. So therefore, so what you can do though is that once you learn your system, then you can apply to a test set. You can call it a test set. For example, you saw that I applied to 2 proteins, different proteins that worked. So that way you can think of that, you keep something separate on which you will apply your model to see whether it is working or not. That way you can divide into train and test set.
But how do we calculate and estimate?
Efficiency of the model, we know how correct your predictions are for how many proteins. For example, I have tried that on this particular system and it is working. I will try it another one, it is also working or not working. Based on that, I will get to see the efficiency, how fast it is. So it all depends on how best it's working. When you are coming up with a self-driving car, so how many situations, how many different bottlenecks it can overcome, how long it runs without crashing, it will give you some of its efficiency. Okay.
With that, we will stop this particular talk. Thank you, Arnab. Thanks a lot.
Okay, so the next talk, as Sutit mentioned, that the actual speaker could not come because of health reasons. So instead, Professor Sutit De is going to give the next talk. And just to give you a brief introduction of him, first of all, he is the main organizer of this particular AI event at IISER Pune. He is a professor in biology department. He works in ecology and evolution. Did his PhD in JNCASR, and then immediately after PhD, he joined here in 2007 as assistant professor. So, and he also, is an active, I would say, proponent of AI initiative, and recently he gave a very beautiful 3-day short sessions, lectures on how to use AI in research, and many of us got extremely benefited from that. So something like that, he is probably going to talk here also. And he also did some workshop for 2 weeks, no? 2 weeks, and there was a very useful workshop. So I am sure that you will get to learn important things of how to use AI in your research or even other activities. With that, I will give it to Sudhit.
Thank you, Arnav. Thanks. Okay, so as Arnav mentioned, I was not supposed to speak. I'm here because I'm facing one of my colleagues. And the primary reason for that also is that this was supposed to showcase our faculty's work on AI. And I do not work on AI as a scientist. I use AI. And more importantly, I'm very, very interested in policy matters related to AI. So I also happen to be heading the AI committee at IISER Pune. And as part of that responsibility, me and my colleagues, we actually looked at a lot of things, a lot of writings, and many, many other kinds of documents about how exactly is AI being used in science, in other areas, and of course in the context of teaching. So what I will do is, I won't bore you with all the policy jargons, etc. What I'm going to do is, I'm going to give you some very personal reflections on what exactly does it mean to use AI in research and teaching, what are the pitfalls, and what are the things that you as students need to be aware of. So I'll start by talking about, very briefly, what are the places where AI works. And I'll talk about what are the places where it does not work. And then I'll quickly tell you just 2 or 3 things, or maybe 4 things perhaps, which as students, as researchers, if you keep in mind, then your journey using AI is going to be much more fruitful and probably much safer. So where does AI work? So in the context of a place like IISER, where both teaching and research happens, it aids both in terms of research productivity as well as in terms of teaching and learning. In terms of research productivity, when it comes to reviewing the literature, when it comes to finding out new articles, AI is actually fantastic. I'm not really talking about going to ChatGPT and just asking, hey, what are the latest papers on such and such topic? I'm talking about using more involved and much better platforms which use LLMs as one of the part of their whole process, agentic process, in order to reach the literature. And in general, it has been our finding that such platforms very often do a pretty reasonable job of finding literature, which otherwise will take much longer for you to find. Secondly, in terms of generating new ideas or checking out new ideas, it's actually very good. For example, I'm sure many of you might have heard the name of Professor Terence Tao, who happens to be one of the foremost mathematicians in the world. And Terence Tao reports that he actually able to get very good quality stuff done using AI. And if AI is able to act as a brainstorming partner for Terence Tao, I think it will work for most of us, right? So in general, if you are prompting AI properly, that is the key over here, then you can really use it as a bouncing board for your ideas, which very often is a very useful tool for any researcher. The third thing where AI is used a lot in terms of coding. Now, coding actually can be thought of at 2 different levels. One level is where you are, let's say, working with Professor Arnab Mukherjee or Professor Bedarth, and they tell you, hey, write a code to do this. In those cases, many students nowadays are simply going to ChatGPT and saying, hey, do it for me. And when they're doing that, they're getting a code which sometimes on the face of it, it works. But when you actually do pressure testing, when you actually try to look at the edge cases, many a times it fails. So in all those cases where the code is the ultimate product, there telling AI to do it for you is probably not a great idea. Even in the context of places like companies which use software as a service model, so for them making the software is the big thing, when obviously they are using a lot of AI in their coding too. But it is becoming clearer and clearer that when lead developers or developers with lots of experience are using AI, they are able to get results that are good, decent, usable. But when people with very little experience, and more importantly, people who are not checking the output at all are using it, then things are becoming a little scary. Many a times, the code does things that nobody has any clue why it is doing what it is doing. So, my personal recommendation over here is that if you are training to become a theoretician, there is still some merit in trying to understand how coding works, and at least going to a level where you should be able to look at a 1,000-line or a 1,500-line code and figure out for yourself what exactly is happening with the code. If you are not doing that, then there is a problem. There is a chance that AI will come back to bite you, and every people are using AI for coding will have their own set of horror stories about it, which very often doesn't get reported in the press, but when you talk to them over a cup of chai, you actually get to hear all those stories. So for that kind of coding, where coding is your main business, be very careful. It is even companies like Google and Facebook, even they are seeing that many a times AI written code is not really scaling. Which means that it's good for a quick prototyping, but when they're trying to ship a product, many a time it's not really working out. However, where coding works fantastically, suppose you have to make a quick small app for yourself, in the context of your research maybe, where you have no intention of shipping it, where you know your problem inside out, and you know for a fact that if something goes wrong, you will be able to figure out very easily. In all those cases, making simple apps for yourself, that is where coding, vibe coding using AI absolutely shines. These are cases where the cost of failure is much lower. The cost of failure is personal. In those cases, say that it's a very good and legitimate use case, and this is the kind of stuff that we are going to talk about in the session just before lunch, where an IISER Pune alumnus is going to come and quickly teach you how to make very simple apps on your own. In the context of teaching and learning, AI has actually played a very positive role. So for example, virtual teaching assistants, custom GPTs or GEMs on the Gemini platform, if you are able to make one of those and then use it again to learn certain topics, really helps. One of the ways in which it helps is that it gives very nice feedbacks about the mistakes that you are making, and even if you are a teacher, it allows you in many cases to personalize things to a degree which is much greater than what is possible in a human-to-human interaction. And again, as a teacher, I personally have used it for curriculum enhancement. I've used it for question making. If you are checking the output thoroughly, if you're checking it properly, many a times you actually end up getting really good results here. And finally, and this is where I think it really shines, not everybody learns similarly. As teachers, we know. Some people need a little more time. Some people learn through abstractions. Some people learn through examples. Some people learn mathematically. So for all those people, it's very difficult for, let's say, a classroom interaction like this, for people to tailor it for your needs, whereas with AI, you can actually tell it by give me examples, or give me the main points and give me the overall conceptual landscape of this. Those kinds of places, AI actually does a very good job in telling the students or teaching the students. Also, language. Ours is a linguistically very diverse country, and we each year get lots of students who are absolutely superb, sharp, but they have problems in terms of English. And in all those cases, these students, I personally have interacted with them, they find that learning from AI is actually helping them a lot in moving that language barrier. So I'm not going to talk about which platforms to use, etc. We can discuss all those outside. But in general, my personal experience of pressure testing AI is that if the thing that you are trying to learn is reasonably simple, let's say at a BSc first year or BSc third year or even up to MSc first year level, in general, AI does a very good job in teaching that. However, when it comes to ultra complicated concepts or really, really advanced concepts, sometimes it ends up, the results ends up being a bit iffy. But in the cases that I pressure tested, I can assure you that in those cases, even many teachers are going to find it difficult to explain those concepts. So I'm not really going to hold that against AI in that particular context. So where exactly can AI become an issue? So I'll divide it into two levels. One is in terms of what I have called institutional, and the other will be psychological. So of course, nowadays it's very difficult to give any assignments to students because whatever we do, there's a very, very high probability that the students are going to simply dump the entire thing into a chatbot and take the answers out and give it. We keep on telling them that, look, if you do that, you are actually digging your own grave. They say, yeah, right, thank you, and then do it anyway. How do we know? No, because we give questions that otherwise we don't even expect you to solve, and suddenly 95% of the class has solved it with great accuracy, and almost all the answers are looking identical. We know, okay, we just know. So, the other problem that is happening is they are realizing that many, since they are getting the answer from AI, they are not really spending any time in grappling with those concepts. They are essentially their ability to bug up. And when they are doing that, then that is greatly their understanding of the topic. Again, how do we know? No, because they have written a great answer, but when we just ask them some question, not even taking them much away, just ask them in that context, can't say anything. You just change the words. You don't even have to change the concept. Change the words and they're gone. So this actually has become a big problem with those students who are using AI to a great extent. We know that all kinds of softwares exist, which is that they will detect AI, but none of them can do it with a degree of confidence that will stand up in a court of law. That's a problem. We know that, students know that. And the issue is that because of that, students feel, what will happen? Do it. They won't be able to catch me anyway. Even if they catch, they can't prove it anyway. And given all these things, the question that many students are asking these days is, why exactly do I go to the class at all? I sit on my bed, I play video games throughout the day, and somewhere towards the evening, I will just ask ChatGPT, hey, teach me quantum mechanics, and ChatGPT will teach quantum mechanics. Done. Okay. This is actually something many students are feeling, and I hope I'll give you a quick answer when I talk about the psychological issues about why exactly you still need to go to the classes. And here comes the biggest thing that many people are actually asking. If ChatGPT is going to teach me everything, then why do I do this? Place them. Okay. Now, why exactly do you think you still? And before you answer that question, please appreciate that everything that a teacher teaches is already there in books. And all the books are already there in the library. There is hardly any teacher who is teaching their original research, right? Of the time, at least in the lower classes, we are teaching stuff which is already there. So, this part, why exactly can AI replace the teachers? What are the costs and what are the benefits? This is something that we actually looked at in some amount of detail. Because this was a very good question and it deserved a reasonable answer. So, I'll come to that answer in a few minutes. But one of the things that we are finding that is happening amongst our students, and I don't mean IISER Pune alone, I also mean the other students that I'm interacting with, is that most of them have over dependence on AI and AI tools. It is becoming the new smartphone. Okay. Don't have it, you almost get all symptoms. And the issue that is happening also is that because the AI tools are available, that the expectation from them has become high. And that actually is of many. So how on earth am I supposed to know all these things on my own? And because of that, I mean, many of you might have known, right, that in many companies, the entry-level intern jobs have all disappeared because of AI. And because of that, when people are writing, sending CVs to professors, etc., they feel that they need to do a lot more just to get an entry. That, unfortunately, in certain contexts, it has already become true, and it is putting an undue pressure on our students, which, personally speaking, I really hate. And a big issue that has happened over here, that people who are using AI, they are essentially AI as managers would use a tool. So instead of creating something on their own, they are essentially just saying, okay, AI, give me 5 different ways of doing it. I will choose solution number C. In other words, instead of being creative, they are becoming managerial. And this thing, remember, nothing wrong in being managerial. Of course, at some point in your life, all of you will become managers. Just that being a manager requires certain kinds of mental training, it requires some certain kinds of domain expertise, it requires certain kinds of maturity, which, when it is being thrust upon very, very young students, is actually some kind of a cognitive dissonance. In other words, students nowadays are being forced to do things at an age where they ideally should not have been. Now, what is the issue with that? The issue is very simple. When you are doing something on your own, when you are putting in your own effort, you tend to develop a liking. That is why, you invest in your relationship. What does it mean? It means that you put in your time, you put in your effort, you put your mental energy, you live with that thing. Then you are going to like it. But what is happening with AI? AI is taking away all that friction. AI is simply saying, hi, here is the question, here is the answer. Done. So because of this thing, the sense of ownership that people have in academia, because they have spent a long time with their problem, because they have thought about their problem, that sense of ownership is disappearing. People now think, the question, I have to reach the answer, AI helps me reach the answer, done. Over. Now this, I feel, is going to be the burnout issue among students. Don't fun with your subject. If you take your subject, then the chances that you are going to keep on doing that thing, related to that thing as you go forward, will go lower. And because of all these things, the other problem that is happening related to the social aspects of formal education. Again, think about it. All the information is out there in the it's even before AI came, it was there on Google. It was there on Google. So why exactly school? Why did you go to college? You went there not merely to learn the subject. You went there, learn how to interact with other human beings. Went there to learn social skills. Went there to learn many, many other things, mental properties, which distinguishes you from being a simple to a productive member of the society. Now, what AI is doing in many cases is it is taking away all those human interactions. And because taking away all those interactions, you are not learning that. If all you are doing is typing on a chat window, then that doesn't require any kind of learning of social interaction from you, and that can actually have a very, very bad impact in terms of how you go out to the society and how you interact with the rest of the society. So this last part is a big answer to the last question over there about whether AI can replace formal education at all or not. My personal view, I don't think it. So, given all this stuff, I thrown you a lot of big things at you. What exactly should a student? Again, this is a very, very personal reflection. You have to censor it in your own wisdom. So, my feeling is that you need to think of AI as an acquaintance who is generally sharp, but once in a while can make massive, massive mistakes, can be really problematic. Given this scenario, you have two choices. You can either decide that you will not use AI, and that's perfectly fine. Okay, there's nothing which says you have to. There are lots of people even today who do not use, for example, smartphones. And as far as we can see, they are leading a fantastic life, in many cases much better than those people who are using it. If you want to be in that category, it's fine. Nothing is stopping you. Don't go by the social thing that, oh, if you don't learn AI, you are going to die. You are not. But if you decide to use AI, then here are 4 personal recommendations. First recommendation, don't go to AIs directly. First solve this is for students, by the way. I'm not talking to the general public, for the students. If you get a question in your assignment or exam or something in your head, don't just go to AI and say that, hey, what is the answer? First, put your own brain. The joy of finding things out, as Feynman said. First, try to get that joy, get the answer, and once you have got the answer, then go to AI for brainstorming. See if there is something extra that AI can give. And use it to improve your work. Get your work done. And particularly when things related to grades, marks, etc. are involved, unless your teacher or supervisor is explicitly saying that, yeah, it is okay, please don't go there. In many cases, if are only good at using AI and nothing else, then it is very easy to replace. Therefore, become good at doing the thing that AI is doing. And this is very important. Everybody tells this, but nobody really does it. You have to really, really, really check what every AI is telling. And when I say everything, I mean everything. Sometimes the errors are factual. These are relatively easy to catch. But in many, many cases, the errors are that of nuance. And those are much, much more difficult to catch. To train yourself to do this. And finally, many people are a little confused about when to use AI, when not to use AI, etc. Remember this thing that you need to attribute AI wherever you have used. And if your use case is such that you will not be able to attribute AI, then know that something is wrong. Know that there is probably a big ethical issue over there because of which you will not be able to attribute AI, and therefore probably you should not be using. So that's about it. Slightly I have taken more time than I intended to, but I'll stop here and take any questions. Yeah.
Thank you so much for the talk. So you talked about how students should use the AI tools and not use AI tools. One of the things is that I myself have used ChatGPT for complex Olympiad level problems, which are especially for the school students, and I've seen hallucination AI doing that. So my question really is it a wake-up call for the education system as a whole, wherein they should be able to frame the questions in such a way that the ChatGPT doesn't give answer, rather than asking the students, because with all kinds of pressures, students are anyway going to do the same things.
Yes, this is something about which a lot is being talked about, that design the whole thing in such a way that AI will not be able to do it. Students are forced to do it on their own. So my problem over there is I've actually tried doing it. And my problem is that if AI is able to solve millennium problems, or is at least able to do things which is leading towards solutions of millennium problems, what hopes do we have of creating something at an appropriate level for undergrad students or school students which AI will not solve? We might be able to come up with, you are aware of probably Humanities last exam, right? We might be able to come up with such problems. But will they be appropriate for a, say, bachelor student or a master's student? I have not been able to find till date, either through my own work or through anybody else's work, level appropriate questions which AI cannot answer. I've been able to find questions that AI cannot answer. And that is the problem. That is why, although a lot is being said that we have to do that, I, frankly speaking, have come to the conclusion that practically probably it is not possible. One over there.
Hello, sir.
Yeah.
I had a question that while teaching methods, can there be a way that the teaching methods is in coherence with AI? Means, for example, while teaching, one can teach how to use an AI to find an answer. Means how to brainstorm with the AI. That can be done in school level itself, so that student understand if they are supposed to use AI and how to use AI.
Yeah. So you are right. That is something that is needed. Okay. But the point is that is going to be just one course. Since I have given a course like that, I can seriously tell you that that can be done reasonably well over, say, 2 to 3 weeks. You don't need any more time than that. And this is something that is going to be transdisciplinary. So I don't have to do it separately for maths and chemistry and physics. I do it for one and it works for all. So that is definitely needed. We like it or not, that will come. That has already started coming. It will come in a bigger way, and at some point, the education boards are going to incorporate. Just a matter of time.
Thank you, sir.
There is something over there, and I think we'll stop with that one. Anything in Zoom? Oh, there's something in Zoom. Okay, so I'll then maybe take one from Zoom.
So, Nishya Jajodia asks,
yeah.
Given that AI systems are trained on human-generated data and established knowledge, to what extent can AI contribute to research in unexplored or poorly understood scientific domains?
So, even if AI has been trained that way, AI is capable of coming up with new hypotheses, or it is capable of coming up with new ways of dealing with problems. So just because the training data is human, that doesn't preclude, given the way the technology operates, that doesn't preclude going beyond the training data, number one. And number two is, we have actually run out of data to train AI on. So nowadays, a lot of training of AI is actually happening on synthetic data. So just to give, yeah.
Yeah, thank you, Sudhir, for the talk. I'm glad that this got accidentally incorporated today, but it's very useful.
Tell that to Shalini. Yeah.
I'm wondering about your thoughts regarding changing nature of assignments and assessment in the age of AI. Because if we want students to use AI productively in their assignment, what can we change fundamentally about the nature of assessments and assignments?
That is the problem with this. Okay, there are certain which, if you just give it an assignment question, which will not give you the answer. It will say, okay, let me take you in the correct direction. And then it will quietly nudge you in that direction. So those kind of tools are very, very useful. But the issue is that how do you ensure that the students are accessing only that tool and nothing else? So something has to come from the side where they have to realize that, look, if I use this tool, my long-term learning is served. If I use that tool, then short-term, I will get time to go and watch a movie, but long-term, I am dead. And that understanding, how to impress that upon students, I think that is a bigger challenge right now for educators. Okay, thank you very much. We'll stop this session now. we have a quick break and we'll come back at 11 o'clock. There is some tea outside that is on us. There's also some sandwiches that is on you, that is on payment basis. And feel free to catch us during the tea break. Okay? We come back at 11 o'clock. Thank you very much. People settle down, please. Settle down. Okay. Are going to start our next session. And the first speaker in this session is Dr. Chandrakala Meena from our physics department. So Dr. Chandrakala Meena joined our physics department in May 2025. And prior to that, she was a faculty at IISER Tiruvananthapuram from December 2022. Her research focuses on understanding the macroscopic behavior of complex systems and their robustness and stability by integrating nonlinear dynamics, network science, and machine learning approaches. Dr. Meena.
Thank you very much for the introduction. So, as you told, like my area of research is like determining the macroscopic behavior of the large complex system using the dynamics, network science theory, and AI tools. I will go through like what are the problems in the complex systems and how the AI helps. So generally in today's talk, my particular focus is like how to find the hidden patterns in nonlinear time series AI approaches. So basically we try to understand the macroscopic behavior of the various large complex systems, and we assume that we can understand this macroscopic behavior of the large complex system by understanding the microscopic description of this large complex system. So under this microscopic description, we assume that the large complex systems are made of many interacting elements, and the interaction among these elements are governed by the law of, by the physics laws. So for some system, like there are defined physics laws, but for some complex systems, still like we are figuring out what are the actual driven mechanisms for different kind of complex systems. But generally in our nonlinear dynamics theory, we assume that we can track the activity of each element which are in the neuron by this kind of differential equations, where the first term is corresponding to the self dynamics, and the second term is corresponding to how the interaction is influencing the activity of the each node in a large complex system. So when we study only just the single unit of a network, then they can follow different kind of patterns when they evolve in the time. So that evolution of the nodes activity with time, we say that this is like time series data. Okay. And the real system are not like follow the linear time series data. They have the complex behavior. So we generally see the nonlinear data with the time. So this nonlinear data can take the form of the periodic or chaotic or hyperchaotic. Okay, so this is the one problem, like how we can identify like whether this individual element is following which kind of dynamics. So today my mainly focus will be on this, but I can also introduce there are other problems that exist in the complex systems, like when we study collectively the activities of all elements in a network, then they follow some patterns, like whether they are randomly behaving or whether they are partially synchronized or whether they are fully synchronized. So this also like if we know the models, then we can write this set of equation, we evolve, we do the simulation and find out the patterns. But for the some system where the equations are not there and we cannot, then like it will be it is difficult to like predict this collective behavior of the network. So this is the these are some problems. So particularly I will focus today like how we can identify what kind of dynamics this nonlinear time series has. So there are some traditional methods, like you can find out the Lyapunov exponent. Lyapunov exponent is nothing but you evolve the system by starting two different initial conditions. There are two different initial conditions are slightly different from each other, and we see the gap deviation in this trajectory. If this deviation is grow exponentially with the time, then we say that the time series is chaotic. If it is not growing or shrinks toward, then we can say that the system has the fixed point dynamics, and it is constant, then we can say like periodic oscillator. But this method is valid when there is like a dynamic equation corresponding to the real system is well defined. Similarly, there are like Poincare section method where we can put a section in, suppose a system is n dimensional, then in n minus 1 dimensional we can put a section, and the trajectory will evolve and it will cross that section, and we can observe those points, how those points are behaving. According to that we can identify. For example, if this trajectory is evolving, if it come back to the same point, then we can say it is periodic behavior. If we start from here and it is taking different path or different points on this section, then we can say like aperiodic behavior. But again, this is the problem, like we have to know the exact differential equation, then it is like correctly we can identify. There are another methods also like recurrence patterns. So generally when we see the cloud, we see that today there will be no rain, and if we see this kind of cloud, then we can say, oh, there is a chance that today we can see the rain. So like why we say like that? Because we are like observing again and again similar kind of patterns. So the idea comes from these recurrence patterns. So when we observe the real data corresponding to a system, we have this just single time series data. So like, but the data is not influencing by one variable, it is by influencing by several variables. So first we have to find out all the variables that are influencing that time series data corresponding to one activity. For example, temperature of a particular location. It is not influencing just temperature, it is like humidity, pressure, all these things. So like we have to find out that how many variables are influencing those data. So there are some mathematical methods like Tekker embedding theorems by which we can find out the embedding vectors. And then we can generate this phase space trajectory actually. And from the phase space trajectory we can find out these recurrence patterns and some recurrence network structure also. So these black dot points are like the state is recurring, and the white dot is like state is not occurring. So this the recurrence states are captured by these recurrence plots. Okay, so like for example, periodic cycle, the reconstructed attractor will be like this periodic cycle, and the recurrence plot look like this. For the chaotic, the recurrence plot look like this. For the hyper chaotic, it is like this and this. But their problem is that, for example, this different system, Lorentz system, Rosler system, these are the different systems which correspond to different models, which mimics the behavior of the different real system. So you see, like all these are the chaotic trajectory, chaotic time series data, but the patterns is different. The phase patterns also different. Then the recurrence plot also will affect, because we are calculating the deriving the recurrence plot from the phase space trajectories. So like just observing the recurrence plot itself, we cannot identify whether the data will be the nonlinear time series is chaotic, periodic or noisy. So we have to extract some features. Now what are those features? The features are like how like density of the recurrence points, the maximum length of the diagonal line, the maximum vertical length of the vertical lines. So these kind of different features we measure. Similar features we can measure from the recurrence this network. So the global properties like average path length, average global clustering coefficients. So different features are there. So now question like corresponding to different system, even though the same behavior, but recurrence plots are different. So for example, if you take the time series, and suppose you are finding the recurrence rate like density of the points, and you are getting the value 0.06, that is like corresponding to the chaotic trajectory. And if you take the periodic time series, then also you can get the similar like 0.06 recurrence rate. So just by observing this recurrence rate, we cannot classify whether this is periodic or chaotic. Then we have to look another features. For example, if we see determinism, we can say, okay, this is like chaotic because this points is corresponding to the chaotic. But again, you can see this entropy. Again, we are getting the same value for the periodic and chaotic. So like from this recurrence measures also, we have to take the permutation combination of all the features, then it is difficult. So here like machine learning can help us. So how the machine learning can help us? We can take this all the recurrence features as an input to the machine learning model, and then we can train these machine learning models. So like the time here like data is limited, so we can use the standard ML models. And what is the problem here? Like in the machine learning, there are different kind of problem like classification, regression. In classification problem, like we have to categorize the classes into different class. So here like our problem is like whether the time series is periodic, chaotic, noisy or what kind of. So it is like classification problem. So in the like, and since our data is labeled, so we can use the supervised machine learning algorithm. And in the supervised machine learning algorithm, these are the standard supervised machine learning model for the classification problem. Although all models like logistic regression, support vector machine, random forest all help us to classify the different type of time series. But I am using this different ML model because their algorithm is different. For example, this logistic regression classify different classes into different categories based on the probabilities. Here like we find out the planes between different classes. So corresponding like this support vector is like geometric approach. This random forest approach, like we take some sample data, create different trees, we create different trees based on some different sample data, and then majority of the like the different trajectory will give different results. So the majority will wins. So final result will depend like what the class is supported by the majority of the decision trees. So say like same task but by different machine learning models, and different machine learning models means their algorithm is different. That's all. So we use those machine learning, feed these input features, and we can classify this single time this into different, whether this is chaotic, periodic, noisy, or chaotic. Now the next question is that, okay, we implemented some machine learning models, but how much, like which model is good or bad, or how we are like correctly classifying whether the our different kind of classes. For that, like we have to implement the evaluation matrices. For that, like first we have to think about the confusion matrix. So this is like, here we are having 4 classes. So for the 4 classes, you can extract the confusion matrix. For the simplicity, I can tell you the confusion matrix is corresponding to 2 classes, whether the class is periodic or not periodic. So like we can, so like suppose this is like our predicted class, this is accurately class. So this TP means like periodic class we can assume at positive class, and it is like positive periodic class is correctly identified, so true positive. So FP means like we predicted that class is positive, but it is not actually positive, it's like not periodic. So in this way we can define this TP, FP and FP, and we can evaluate different matrices like accuracy. Out of total predictions, out of total prediction, how many predictions are we made correctly predicted. And in this way, like different evaluation matrices are sensitivity, precision, specificity and F1 score. Now there are also conditions like our data is balanced, then accuracy is sufficient to check the performance of the model. If data is imbalanced, then we have to check the F1 scores also. And then we can like we can find out the per class accuracy, or we can find out the overall accuracy of the models. So corresponding to each classes, like we can take the different machine learning models and check the these evaluation matrices. For example, for our cases where we classifying 4 classes, the logistic regression is giving overall accuracy 86.7%, random forest 95, and support vector is 90.3. So we can say that for this classification problem, the random forest is the good classifier. So in this way, like we can identify which model is the good classifier for a particular kind of problems. Now again, the different thing is that suppose we don't want to calculate this recurrence measures. Directly we can take this recurrence plot as a machine learning model, and we can classify whether the time series is periodic or chaotic, noisy or hyperchaotic. So that also we can do, but for that we have to implement the different kind of machine learning models. So there are deep learning models. In the deep learning models also there is convolution neural network model, which is good for the image kind of classifications. Okay, so in the we take the images and we extract some features from the images, So there are different layer of the feature extraction. First, like it will identify small features in terms of the points and small lines. And then we go to the next layer, then it will capture the large portion of the images. And at the end, like it will capture all the features of the full images. And that features we can input in the standard deep learning model, and then can assign the probability like this image is corresponding to what animal, like for example in this. So that also directly we can also classify. And once our model is trained based on the synthetic time series data, then we can implement this trained machine learning model to identify the time series of the real data also. For example, in our cases, we take the real data of the different light curves and some experimental data that we generated from the electronic circuit. So that again we can plot, or we can take the time series data, recurrence plots, and give them to our trained machine learning models, and it will help to us to predict the correct dynamics of the real time series data. So either you can give the image to the deep learning models, or you can give the features to the like standard ML models. So these are the different real data that we predicted based on our trained machine learning models. Another thing is like there are different kind of input features. In among these features also, some features may be more important. So this problem also we can solve, like which feature is more important. For that also there are some models which can implement. For example, in this particular case, the random forest classifier, and we find out that this average path length is more important features for our problem. Then this is the second important features. This is the like least important feature. So the time series is prediction, the dynamics of the different time series, which features is playing important role to determine their dynamics. Not only this like we are so far like I do like how we can predict the dynamics of the single unit in a network. Another problem is like we can also help. We can also take the help of AI to predict the collective behavior of all the elements. There are 4 different kind of algorithms are there. For example, people have been doing exploring many things. So far, like people have explored a lot for using the reservoir computing. For example, this is the network structure. So this hub node, this is like center node, which is connected to so many peripheral nodes, and these peripheral nodes are connected to only to the center nodes. And in terms of the dynamics, you can consider that each node activity is influencing by 3 variables. So like corresponding to each unit, there are 3 variables. So this node is different and these nodes are identical. So we can take the 2 reservoirs, and corresponding to 2 reservoirs, we can take the 2 different inputs. For example, this reservoir is corresponding to hub. So in this input, like the activities of this like internal dynamics of this hub node, and the on an average, because of this interaction term, there will be the on an average effect of the nearest neighbor nodes, and that we can take like here. And in the like model, when we do the modeling, there are intrinsic dynamics that we cannot change, but there are the external parameters also that we can tune externally, like globally. So that parameter is corresponding to the epsilon. So that epsilon also we can give as an input. Okay, so first we have to think like microscopic way of the large complex system, and then how we can give the input to some machine learning models. So, and we can train this reservoir, and then finally we can get the next time series point. So you see, if we change this external tunable parameter, that is like here coupling strength. So as you vary the coupling strength pattern, the patterns are varying, and this is like when we solve the model, and this is like when we capture using reservoir computing. They are almost identical. So this kind of problem also exists following this. There are like another kind of problem. Suppose sometimes here are the real system, but we don't know what are the actual dynamics they follow. So there are many machine learning models which are going on, like Cindy. So in this, like and in the reality, like so far in the model we assume that the elements in a network are connected in the pairs, but in reality the entities can interact in a group also. So corresponding to the group interaction, what will be the dynamical equations? That is the question. And in group, and if the elements follow the group interaction, then how we can define the network structure? That is also a problem in nonlinear dynamics and complex system. So like there is some methods from the pairwise interaction dynamics, we can extract the time series data corresponding to each element, and then we can pass those time series data into the machine learning or AI models. And that AI models will give the weightage corresponding to the permutation combination of all the variables like x, y, x square, x cube. Then like we can like identify the actual dynamical models, time series data and the AI models. We can also construct the connection among the elements in the networks. So these are the some examples there, but there are many more problems like to determine the stability. Suppose we want a particular type of collective phenomena corresponding to the complex system, then how we can trigger the external tunable parameters so that we can get some targeted states. So these are the different problems exist, and these days like many people are using the AI models to solve these all kind of problems. So not just the limitation here to that AI can help to predict the dynamics of nonlinear time series, can help to predict the collective behavior also, stability also, robustness also, and like control mechanism also. So there are like many models which have been emerging from the last some of years and the evolving direction. So with that, I would like to thank my lab members and my collaborators for particularly this kind of work, G. Ambika and my student Thakurana, and different funding agencies.
Thank you, Chandrakala. So, are there any questions over here? Okay. Yeah, with that.
Thanks for the nice talk. So you showed like one way where we can use a CNN for the classification directly from the recurrence plot, and another way with features, and has tried using together like having like
Yeah,
a CNN
we tried, but like when we use the deep learning model, then like computation heavy that. But when we calculate the recurrence matrix, also there are some problem with the formula we use. So, but when we tried both the performance, then find that our model, the deep learning model, are correctly classifying the.
So, anybody else? So, I have a query in this context. Have you looked at those time series which is not being correctly classified by the deep learning models, and have you looked at or compared those with the ones that are not being correctly classified by the other processes? Are the same kinds of time series not being correctly classified by both, or is there some kind of a difference?
Actually, surprisingly, when we were using learning model, most of the real-time series we are able to correctly identify. But we are like exactly we are not using the convolution neural network. We are using the RichNet 15 classifier, which is like based on the CNN type of algorithms. So again, it depends like which CNN, like in the standard machine learning model, there are different kind of algorithms. The CNN also, like image classification problem, like there are different models. Even though they are based on the CNN kind of algorithm, first they will extract the features, and that features they will send to the fully connected layer networks. So it depends on two things, exactly deep learning classifier model you are using. So we particularly tried one deep learning classifier model, and in that like we are correctly classifying. But again, we sent this paper in the review, then the reviewer has like why the model is like so much correctly identifying. So
Yeah, that's the problem.
that
these
we are
days.
like exploring why it is like correctly classifying. Even the whatever the real data you give, it is like mostly correctly identifying correctly.
Good. Okay, thank you. Thanks a lot. Yeah. Pranay? Yeah. So our next speaker is Professor Pranay Goel from the biology department. In his PhD from the University of Pittsburgh in 3, and after a couple of postdocs in the US, he came back to India and joined IISER Pune in 2009. He's interested in studying biological systems using mathematical, which means analytical, computational, algorithmic, whichever way he can think of, approaches. His main focus areas are mathematical physiology and type 2 diabetes. He's also interested in data science and predictive modeling for healthcare and precision medicine, and that's precisely what he's going to talk to us. Pranay.
Thank you. It's on. Thank you, Steve, for the organization and for the invitation to speak here today. I want to talk to you about some of the work that we are doing in precision medicine in using AI in our lab. So I'm going to give you 2 case studies that I hope will explain to you what it is that we do and some of the problems that we work on, and it hopefully will generate some questions about the work, and I'll be happy to take questions. So the idea behind precision medicine is to ask, okay, what can we say about in medicine? What can we say about a person's diagnosis, prognosis, or things of the type that can be useful clinically? And the question that we are asking is, we'd like to be able to make decisions or like to be able to support decisions for individual people. Well, that's an interesting question, because when you look at data collected from several people, and you could take, for example, an average behavior, well, that's describing a population. How much of that data, how much of that analysis carries over to an individual? That remains a question that often gets asked in the form of a word called precision medicine. Can we target decision making? Can we target decision making which is directed in the sense that for certain groups of people, certain types of medication would be appropriate, and for other people, other kinds of medication. If we are able to describe the targeted therapeutics in a way that is best for particular subgroups of people, then that would be precision medicine. So that's the goal. My first that I'm going to talk about, the first problem that I'm going to talk about, is a method for bone age assessment in Indian children and adolescents, called this DigiBone. And this was work done along with Dr. Anuradha Khadilkar at IISER Pune, and with Karolinska Institute, and my student Shreya Chakladar at IISER Pune. These are all of the collaborators that have worked with us on this problem and continue to do so. This work's been carried out for over 7 years. Written several papers on this, and I'm going to describe this system as it stands now. So the question is this: we'd like to be able to understand how a child is growing, and one of the best measures for understanding that is to look at the X-ray. When I say we, I mean our collaborators, our clinician collaborators, pediatric endocrinologists we work with. The best way is to do this is to look at the X-ray of the left hand in a child and do what's called bone age assessment. You look at the bone structure of the hand, compare it against standard atlas, and ask, which contains images of children of various ages, and you ask the patient I'm interested in, how closely does it match a particular plate in that atlas called the Grulich pile atlas. If it's a plate if the 9-year-old's plate matches this particular X-ray well, that child is likely to be somewhere around. that, on the other hand, matches a 7-year-old child's plate, well, then you probably be better off saying that this is a plate that the hand has a developmental age about 7 years. Okay, so you would ask the question, well, why is developmental age, how can it possibly be from chronological age? Well, the answer is very simple, because children don't necessarily grow according to exact synchronization. Some children may lag behind their chronological age in terms of development. Some may have advanced physiology relative to the chronological. Represents the median that their chronological age would represent. So if a child, for example, lags very much behind what they should have grown to, well, then that helps the clinician make a judgment as to whether or not intervention should be carried out. For example, a child 2 years or more behind what their development should have been at that chronological age, or perhaps they might be a candidate for growth hormone. So in order to get a very accurate assessment of bone age, of the developmental age, one looks at the bone age. And if I might give you a 1-second primer of what exactly are you looking for in the hand, well, it's the epiphyses, the growing parts of the bone, the ends of the bone. Of course, the bone elongates and bone grows and calcification takes place and all of those things. One of the things that people look at is epiphyses, bone structures, the calcium structures, and those have a very marked aging in terms of how they develop in growth. So those are the things one would want to look at if one were a clinician. Well, I'm not a clinician, so what can we do in terms of AI, in terms of bringing AI to this? So first, we ask the question, why AI? Why should we use AI at all? We understand that computer vision is very good now. There are lovely algorithms that we can bring to bear on this problem. So that's one of the reasons. Why we like to solve. The second question is more to do with what exactly are we looking at, or how do we force, or how do we coerce, how do we nudge our algorithms to study the structures that humans are interested in? Well, to that there isn't a very good direct answer. We have an indirect answer, and the answer goes, if you show it a lot, if you show an algorithm a lot of samples, a lot of training images, a lot of X-rays for which the answer is known, then in that case, if the sample size is large enough and the algorithms are allowed to run in the way that weights of the network change, then you expect to have learned something about the network, about something about the images and their labels, and eventually when you try and apply them to data that you've not seen before, you'll be able to get an answer that is close to what the human. So it's a process of training by examples, and this is very nice. It's nice in two senses. In the one sense, it is the standard technology of training a neural network. In a second sense, it is nice because it leverages information that a clinician is able to collect over a period of doing over a period of clinical use, over a period of actually seeing patients, assessing their ages. The clinician, when they do it manually, there's a lot of data that's collected, and we are able to use that data to try and distill the essence of this clinical exercise in terms of the algorithms that we can use in patient decisions. So that makes it very interesting to us. What this picture shows over here is this is an X-ray of a child, and we'd like to be able to make we'd like to be able to say that this is a child that has a bone age of 10 years, because that's the Grulich-Pyle plate. A standard Grulich-Pyle plate would look close to this. At 10 years, they would look close to this. Okay, so let's ask ourselves, what is the training data set that we can use? Well, in 2017, the Radiological Society of North America, they conducted a challenge in which they put out a data set. It's called the RSNA data set. and it has 12,000 images for which to train. This is lovely, and each of these images is well curated. There are 6 raters that have rated each image, so it's very well rated. And an average of 6 raters gives you good confidence that you're looking at nearly correct rating of that X-ray. And using this, we are able to then, so the RSNA challenge asked, can you build a network tool, if you like, that can do this predictive boning? Okay, so that's going to be one of our main data sets for this problem. So a lot of people went in, not us. We came to the table a little later. So not us, but a lot of people went in and built neural networks of various sizes and shapes and so on. The winner of this channel was called 16-bit AI, and they were able to achieve a mean absolute difference of about 4.27. So 4.27 months essentially says that if you calculate the absolute difference between what the human would have said and what the AI says, and then you average it over this entire data set on the test site, then you get to within about 4.5 months of the exact answer. And this is, remember, a population level analysis because you're testing it on about 200 data points. So we decided in our group, working with Dr. Khadilkar and others, that we want to build a system for Indian children. This is the RSNA dataset, I should say, is largely a Caucasian data. Now, if you want to discuss the nuance of using a network for one population versus how we can apply it to another population, I'm happy to discuss it. Perhaps it's a lengthy discussion, so perhaps we can do it offline and one of you can ask me. So we'd like to be able to get to within 6 months in terms of being able to tell the child's age within 6 months. Okay, so that was our goal. We want to do this for Indian children. So we looked in the literature, and if you ask, so we checked on Gemini yesterday, looked it up, we Googled ourselves to ask which are the bone aging software that are available in India for Indian children at the moment. And lo and behold, Gemini seems to know us. So it found us, Digibone, and Bone Expert. Bone Expert is a very well-known software. It is in use several places. I believe it is also used Ruby Hall here in Pune. It's a standard data. It's a standard, almost standard software, and the target population is primarily developed and validated European, North American pediatric cohorts. It does very well. It does an automated Druid file, which is what I've been describing to you. It also does another method called the Tanner-Whitehouse method, and it achieves an MAD of about 4.1 months. We are targeting the Indian pediatric population, and not only do we do the standard Druid file, we have a novel method called the segmental file, which I'll tell you in a minute, and our system has an MAD of about 4.7. So let me show you the basic pipeline that we use in order to leverage the RSNA data. The first column on the left shows you that we're using essentially networks that have been trained on very standard data sets like the image. Others. The second column says that those networks haven't seen hands or X-rays, so want to take those networks and fine-tune them, transfer learn them onto images that have X-rays in them. So X-ray. So we use the RSNA data set in the middle column there, taking a standard network on Reddit, putting it through learning from an RSNA network. And then finally, in the third step, this network that has learned from an RSNA data set, we ask it to learn further on Indian images. So painstakingly, over several years, our collaborators have labeled Indian data, and so we are able to show thousands of Indian images in a final step. So a naive network, having seen only cats and dogs, whatnot, having seen X-rays, the hand, having seen X-rays of the child. So that's our basic pipeline. We developed this and we call it DigiBone. There's an innovation that we built into the system. The innovation is as follows. We divide the hand in certain groups of bones. The carpals, the wrist bones, and the short bones may have matured differently. If there's differential maturation in the hand, perhaps you would like to look at only the bones of the wrist, the ulna, and you might end up saying, well, this is a child of 9 years. If you look at the carpals, well, the carpals look like more belonging to a child of 11 years. If you look at the short bones make it look like 11.5. The question is, should you just average out and give an average age of the child? Perhaps and perhaps not, right? So it's a nuance that we build into the system, and we are able to do segmental, but also full hand rating. So if you look at the full hand rating is. So this is something that we want to carry forward to say that if there is differential maturity in the hand, we'd like to be able to. I think we are the only ones. There's some literature, segmental, but in the way that we are doing it, I think we are doing it in this manner. So this is the interface. We have a little interface that we can use to test all these, to allow people to codes. We've sent out the paper. It's under revision. All of the codes will be available on GitHub. Completely nice. And we hope that this is something that we can now go on to validate in studies. Use it, clinicians can use it, and we hope to understand how it works and how it might improve. So that was my first project that I wanted to describe before you today. The second project that I want to talk to you about is something called SnapMetrics. The SnapMetrics is a arthritis detection program. Again, we'd like to use AI to do. This is developed with Dr. Sanat Phatak, and that's the logo of a company called Med2Measure that Sanat has founded. In fact, it incubated here at IISER, and we are a technology partner that helps develop some of the core functionality of it. So let's ask ourselves, what is the question we are looking to answer? Well, that's my slide that says these are the people largely responsible for it, and I'd like to acknowledge them. Sanat, of course, is all the way in the top left-hand corner, and I am next. So here's the problem. The problem is inflammatory arthritis is a global health challenge, and also as well in India. So there's going to be many people that suffer from these, and there's not enough clinicians, or there's a gap between the patient not having access in advanced clinics. Well, then there's a lot of undiagnosed. There's a lot of suffering, and perhaps we'd like to be able to use technology to bridge some of these. That's broadly speaking what the question we are after is. So we'd like to be able to do screening, analysis, diagnosis, perhaps therapeutics. We'd like to be able to do all of that. We'd like to be able to at scale. Okay, so how should we go about it? Well, I'll show you the solution that we have found. Our solution is this. We'd like to be able to use some relatively simple instrumentation, maybe a box, where you can standardize the photo acquisition of the hands, right? Don't use this side because that side has fingerprints. That's identifiable. We use dorsal side to describe, to try and see if just a photograph can tell you whether you have arthritis. So, and then you push it through a neural network, and perhaps the neural network will show you some of the joints you might have arthritis. Okay, so this is the system we'd like to build. Let me show you where we are. So we've done a proof of principle. This is published a couple of years ago, in which inflammatory arthritis can be detected with reasonable confidence using a smartphone. Simple smartphone, a photograph taken of the dorsal side of the hand. We show that this, in fact, can actually, with reasonable accuracy, distinguish inflammatory arthritis. Okay. Then we went on to ask, well, it's good as a proof of principle. Can we do better? Well, if you ask to distinguish arthritis from healthy controls, then you can actually do quite well. We published this a couple of years ago. And again, I'm flashing these slides. I'm happy to discuss this in more detail. There is a part of question or offline. These are all published papers, so you're happy to take. Very happy to provide you links to these. So that's good. We are able to describe arthritis in some form from photographs. Okay, so we then decided that this was promising. So here's where we are now. We are going to setting up a system in which the taking of the photo is standardized. So that's a little box. It's a relatively simple piece of instrument where there's a light, there's a standard location, there's a standard place to place the camera, and so on. And all you're doing is taking a photo of a hand. The background is white. We're experimenting with various components of this. The idea is to be able to get a standardized photograph. It's relatively inexpensive. Okay, and we are also, well, the company Made to Measure is building a data platform. Figures are shown on the right, where this is done in a very systematic manner, in a manner that respects the ethics of this. Consent is respected. It onboards physicians, clinicians. Data is kept track of. It adheres to the Data Security and Privacy Act that is now in practice in India. So it passes through regulatory approvals, audited, and so on. And this pipeline is now being put in place, for which I think there's about 6 clinicians, pathologists beginning to use working. So this is something that we're going to continue to work on. Not only are we going to try and improve the algorithms themselves, but the entire pipeline of how this is implemented in practice in a clinic until we can get to a point where that's our dream. That's something where we'd like to be. So with that, I think I'll thank you for paying attention, and I'm happy to take any questions.
Thank you, sir, for your talk. When we talk about precision medicine, often we talk about microRNA and multi-omics. When we work on such large data sets, then how do you manage to reduce the noise in the data set, whether it is technical or it is biological? So how you are able to integrate that level of precision in your model or the pipeline that you have created for arthritis to reduce that level of noise to achieve the outcome?
Right. So if I understand your question correctly, you're asking me by analogy to omics data sets in which you're trying to do noise reduction in some sense. What are the sources of error and noise in our system? Right? Okay, so we actually do find that there's a number of places where you might have to correct for noise or improper data collection and so on. So one of the ways in which you might imagine the system degrades is over time, where it's using a lighting system. If that lighting system fails or it has a change in quality, or that might degrade, for example. There's another way in which it can fail. You might have not used the box correctly, and which allows light to come in from the outside, and so maybe so there's issues about using the instrument correctly. There's also issues that the instrument has to be clean, sanitized before another one uses it, and so on. So all of those things are there in this. But from our point of view, we've been able to get around those problems quite well. So we are, in the sense that we notice these problems and we tackle them. So our reproducibility is rather high.
Thank you for the talk, sir. So I understand why you fine-tuned for the RSNA, but I don't understand why you did it on ResNet, I guess. Because
ResNet? So the network that we used for Digibone is a DenseNet 160.
What all datasets did you fine-tune?
We use the RSNA dataset to transfer learn onto images of the RSNA cohort, and we then have a dedicated Pune dataset, HCJ dataset, which we further fine-tune.
I had a question on the for this project. So just by looking at the X-ray images of hands, can we detect the arthritis on other parts of the parts of the body?
So the hand images are meant to detect arthritis in the joints of the hand.
We can't extrapolate to the.
No, we're not interested in extrapolating. We take images, for example, of the knee inflammation.
What question? The model can answer estimate. If yes, is it calibrated in the? Is it sure when on samples where it tends to less error, and unsure on samples where it tends to?
Okay. So your first question is rather easily answered. Yes, we do have an uncertainty estimation. In fact, the metrics that we calculate, we use a trap to define confidence intervals around our metrics with accuracy. The second part of the question is a little bit harder to ask. The question is, if you know the answer with good confidence, the human rating, how accurately does that reproduce? How accurately is that reproduced in terms of where the system does right or wrong? That's it. So let me say this. We believe human ratings are going to be in error at least some of the time. We expect it to be in error, perhaps no more than 5%. Inter-rater variability can be tackled a little bit by going to several doctors and asking them. I think there is an irreducible component to that which will not be removed. I think part of the reason that it cannot be removed is because people look at things differently. Even a trained clinician is going to look at things differently. So I believe that there is going to be about 5 or 10% error. I have some data to that, but we haven't published it. Hedging for a little bit. What should we get rid of that 10%? In 10%, when I said get rid of it, I mean, should they match? If there's an error here in the human rating, should that error be reproduced in the AI system? Well, that's not quite what we want, but that's what the system is effectively doing today. If your labels are in error, you're going to learn that error also in the. Do I have an answer for where I think we should be going? I think we do, but this is speculative. So I'd like to talk to you offline.
Thank you for the talk, sir. Just a question related to what he asked. So right now what you mentioned was you are able to detect like 0.1 to 4.7 months kind of, right? So my question is really the way it seems right now, you are using the pure CNNs, right? So is there any scope for, there is a lot of talk about domains, what they call like domain informed neural networks. So in this case, like biology informed neural networks, can they actually help, and is that something we think may help in making the predictions better? Thank you.
Right. So you're very right in asking us whether we can bring some biology to understand this problem. And that's exactly where we are interested. apart from the pure applicability of using CNN to train these models, we're very interested in asking, can we leverage our knowledge of the biology, the domain, to understand these problems? And in a ways, that's exactly where we want to be. We'd like to be able to say something that is beyond what a brute force training regimen can. So I might give you a partial answer to that. So our exploration of this is to try that the segmental Grolek pile was essentially trying to identify this. That there biologically we know that the hand for some children at least is going to have different. So this is why we started asking this question as to whether we built the segmental growth pile in order to try and address some of these. For example, we don't know how sex hormones can influence the growth of carpal tunnel. There are aspects of it, like for example, the carpal bones, once maturity is reached, the carpal bones are less informative of the aging, because they sort of mature rather soon after puberty, and they're sort of so we are pushing our systems to address some, which is the piece that's informative in terms of making predictions, and in terms of can we understand the biology of development for a particular child, and the biology they have something to say. So we are working on it. I can give you a more detailed answer offline perhaps.
I think stop. Yeah. We'll thank
Thank
Dr.
you.
Goel for this.
Thank you.
Okay. So till now we have been hearing IISER Pune faculty, and now we have a very special guest. This is Aditya Kabra. Aditya Kabra is a IISER Pune alumnus. He passed out IISER Pune in 2018, and he claims that at that point he was pretty much in the same space as many of you might be once you pass out your course, which is, I'm not really sure what to do. So then Aditya Kabra had a very, very interesting journey in the AI space. He is going to talk about it. So I will not take away that thing from him. But essentially what has happened is, as of this moment, among many other things, one of the things that Aditya does is he runs some very interesting AI study groups. People come together every weekend at a cafe near IISER Pune and build all kinds of things related to AI. So he is going to talk to you about his experience, and at some point he is also going to show you, hopefully live demonstration, Aditya? Yeah, live demonstration of how you can make some very simple apps very easily using the simple freely available AI tools. So Aditya.
Thank you very much, sir. Hi everyone. It's good to be back here. So you might have read this story, a simple story of a pottery teacher named Kumar, who also likes to do experiments like all of you guys, and divides the class in 2 parts. And the point of this story is quantity, like instead of focusing on quality, if you can focus on quantity in the initial learning stage, once you start building like your 10th, 28th, 38th project, automatically the quality is going to improve and you are going to achieve success. So I will share it through my own journey. So in 2018, I graduated from IISER and started a small startup called 0+ Labs. It was based on a technology that we licensed from CSI NCL. The focus of this startup was to develop biodegradable plastic products to solve plastic pollution problem. We raised 2.2 CR from United Nations, Department of Science and Technology, Department of Biotech. We had 15-member teams, and like we spent 5 years on intense research and development. We also had pilots with like different partners. But what happened was we committed very quickly to a specific technology pathway and also to a solution. Plastic problem is huge. But after spending 4 or 5 years, we realized that bioplastics are not the solution to plastic pollution problem, and they are not really sustainable. And despite having 1.5 CR of additional funding to us, I decided to close down the startup because I could not understand like whether like it's not a meaningful solution, I thought. So after closure, I was struggling with what I should do next. It was in 2023, and I was exploring various options. A couple of options were going back to my hometown and doing something with family business, like starting a dal mill or opening a construction plant. Or I did my thesis at IISER in theoretical computer science, maths, graph theory, and algorithms. Another option was to start exploring the field of data science, which was very closely related. So I started experimenting with that, taking short courses on Kaggle and deeplearning.ai. But I wasn't sure where it's going to lead to. So there was a conference in Bangalore on AI by Analytics Vidya, and I thought I should go and meet a couple of people who are in the domain. But this thought was there that like if I go empty-handed and if I don't have anything to talk about, then there won't be any meaning to it. Like how would I introduce myself? So what I did was, by taking some short courses on deeplearning.ai, I built quickly, within a week, this small patent summarizer tool. This was my first project or prototype that I was building. And it's a simple prototype. You put the patent link and you get a summary of the claims. When you read research papers, the research papers are written to make you understand. The patents are written opposite way. It's made to hide the information within the claims. So using the summary aspect of ChatGPT, we can get a summarized thing, and I created this simple app. What happened during that conference was, this was somewhere in 2023 August. Apart from speakers and couple of startups over there who were presenting, no one else has done anything related to API integration of this AI thing. And this put me a bit ahead of the crowd since I built something and had hands-on, and two of the speakers agreed to mentor me. One is Dr. Sarabjot Singh, who is a visiting faculty at IISER Mohali, and second is the head of Microsoft Research India. He is leading the department over there. So the point of this is, like, when you do something hands-on and build, you stand ahead of the crowd. Second, after coming back, I started like building a lot of prototypes since I unlocked this new skill. But I was kind of stuck on like, what's the use of developing this prototype? So after a point, I almost gave up that things are not progressing further. I cannot like build a product out of it. Then one fine day, one of my friends, Amay, who is also IISER alumni, decided to visit. And we thought we'll spend a day in nice Pagdandi cafe, which is behind IISER, and spend building different tools. Initially, I was stuck on what to build. After spending a couple of minutes, two unrelated thoughts came up. There was this role-playing workshop on HR that I attended when I was running my startup. It was on like having crucial conversations, like when you had to fire someone or when you had to provide feedback, or how do you like navigate that. And during the workshop, I realized that like I interrupt a lot in front of other people. But the question is, how do I practice this skill and improve it? And another was AI workshop that I attended where they taught us to create chatbots. So I thought, how about I build a chatbot where I can practice this role-playing exercise and try to improve myself. So this was built within like an hour and a half in the Pagdandi cafe. Soon I decided like, okay, I should share this beyond myself. So I messaged the workshop organizer and sent them this link. It turned out that they had a commercial project going on with a Dubai client, and they wanted to take it further in a commercial way. So they asked me to modify it, and that's how my journey of prototype to production started. Initially, I was skeptical on how to build it, but soon there was this new Python library that was recently launched called FastHTML, and using FastHTML, one can develop full-stack web apps just by staying in single Python language in a single file. So that's how I was able to build this platform, and now like the platform is being used by this partner, and they're earning like money in worth rupees crores. So the thing I have understood from like learned from this small aspect was, when I am stuck, I should build, instead of focusing on building an ambitious project, I should just build something very small so that I can build the momentum and get going. So in past 2 years, I have built more than 100+ projects across different categories: chatbots, artifacts, canvas. I always start with very minimal aspect and then slowly get on building full stack projects. And this is how I spend my current day. I try to find some problems sometimes, my own friction, or some projects are just done for learning, exploration, or just playfulness. Then I build something very quick, maybe like within 15 minutes or 30 minutes. Uh, I then share it with others, couple of my friends, couple of my sister, couple of community members. And default, every project is dead. Instead of like I plan to build it further. And if I use it, then only I iteratively add features and improve the app. So in contrast to the previous journey where I pre-committed too early on a specific solution, here I am killing the projects by default unless it's useful to me. And in this way, I have developed like many simple use cases which I personally use and like are also useful for the community. So I'm still uncertain where this path is going to lead to, and I'm like figuring out by building, learning, and sharing and doing small experiments each and every day. So after like doing this for 1.5 years, somewhere around like 6 or 7 months ago, I was getting very lonely and like feeling alone during this journey. And I thought like, why not have a community around like where I can discuss these projects with someone, share my learnings and experiment together. So that's how we started this AI study group in the cafe just beside IISER called class. And every meet, we decide a topic, theme, or a tool, and we meet up and try to build different tools, projects, or use cases around that topic. This was from the mental health workshop that we did with a psychologist from Manipal recently, 2 weeks ago. And these are all the projects that the participants had developed during that time. So just to give a brief overview, our next workshop is tomorrow. The workshop is like if any new tool is launched and if I want to learn, I just post it on Luma and like a couple of people join and attend. So I will share this link with you guys, and if you want to learn about agentic AI, you can come tomorrow and do hands-on practice. But having said that, like this is what we do, but I want you to do carry away with something, because सिर्फ बात करने से एक हद तक समझ में आती है, जब खुद से चीज करोगे अपने हाथों से तब असली एक्सपीरियंस होता है. So I will show you a simple live demo using Gemini Canvas. It's a simple prototype building app that I use very often. I have built around 60 projects on Gemini Canvas in past 2-3 months, and which you can do it on your mobile. And then a couple of our volunteers will be there outside, facilitators, to help you build. Gemini Canvas has some restriction, but the same principle of using English to build digital tools and building your own custom tools and solving your own problems, you can use advanced apps to take it further. So Gemini Canvas, I will just show you brief on what can be done. It can be used to make games, even like music can be integrated. You can even have AI integrations such as image recognition capabilities, like Dr. Pranay Goyal has showed the image recognition classification app, right? So you can at least develop a proof of concept or a demo for that, a dashboard, very quickly. You can also build like custom dashboard and like also visualizations for any concepts or any topics that you want to learn. So let's start with a demo. I was thinking I will start with the first app that took me a week to build, which was a patent summarization app. Let's see in Gemini Canvas how quickly we can build it. So what you need to do is go into the tools, select Canvas, and just type create a patent summarization app. Okay. Okay. Where the input will be patent links and claim summary. So this was one of the problems that we used to face a lot of time in our startup, where we had to read like hundreds or 500 of patent, and the claims reading was difficult. So I thought like a summary app will help, and let's see how it builds. Usually with a simple short prompt, you will get very bad or shitty output, and that's expected. It requires at least 20 to 30 iterations to get to something that you need. And when you provide a good description, good reference document, or some examples, then the quality of such applications improves. So while it builds, I want to do something tricky over here. I'm not sure if it's going to work. Pranay sir has shared a couple of examples in his slide, right? Let's pick his dashboard and see if we can replicate it. I'm not sure if it's visible, but let's try to do it. So this app is ready, and let me open a patent link. Let's see if this works. And on the side, we can try the dashboard that Pranay sir has made and include it in a email. Or so you can add like reference image, and that here you can see the analysis. Right? So I can also share this with everyone. So it's as easy as that. So here you can get the summary and key features. As you can see, the formatting is not appropriate. So what we can do is ask the Gemini to fix it for us. And through trial and error, the app will get improved. So that's for the demo. What I want to do is open your mobile phones. You can download Gemini app and or like go on Gemini in your Chrome and create something using this small simple digital tool. And it has certain restrictions, although it has certain AI capabilities. But if you want to build like fully scalable web apps, there are other platforms like Cloud Code, Cursor, Replit Agent, which you can use. And to learn them, you can join us at AI study groups every weekend at ACAS. And while the second app gets developed, okay, so this is the dashboard that made to measure. So this is like a quick UI that we have built using Turnus's image. And through feedback and through iterations, we can get a better version. I have written a blog post also, which is shared on the resource, which will, once you join the WhatsApp group, you will get them. And this is the role-playing app that I have developed for the client. I will just show you briefly a couple of my past projects quickly. So like a case study will be given, role-playing brief, and based on that, you can like interact with the AI chatbot and do role-playing exercise. And based on that, a report will be generated for you. Show you some. Another project that I developed was Solvit Project Showcase. It was for one of the online courses that I was taking. And this is one of the most interesting projects I worked on. It has been worked on for a year. Like I iterated on it whenever I felt like there's some improvement needs to be done. And what it does was in the course, we had it was an online course on Discord, and the course participants used to send messages on the Discord on whatever projects they used to build. And there were like around 15 to 20,000 messages on Discord, and in that contained like 1,000 plus projects. And it was difficult to extract what message contained project, and the information was getting lost. So I built an AI pipeline, scraped all the Discord messages, passed it to Gemini, filtered whether it contains a project built by a participant or not, and then generated a title and description, very nice description of that project, and then created this dashboard where one can search and filter for different projects. For example, if you need to search for RAG projects, you can get it, and it also has AI integration. Another project that's not working currently is videos idea extractor. I just recently got blocked yesterday night by YouTube, so I could not show a live demo for that. But what happens is, whenever I watch some YouTube video on certain AI use cases by some influencer or some scientist or good engineer, there are a lot of use cases mentioned in that video. And if I wanted to extract use cases that are mentioned, I will have to sit and write down it with pencil. What I did was, I created this agentic application where once I put the YouTube URL, some transcript will be extracted automatically, and then bullet points will be extracted on what are the ideas and use cases mentioned in that project, and then the details will be extracted. And at the end, I will get this nice title and description of each of the ideas or use cases mentioned in that specific video. And based on that, I can write my own notes and comment on it. And this is the study group link that you can click and join. You can join our WhatsApp group. I have made it for specifically today's talk. And we are having the next session tomorrow for AI study group. And there are also lot more resources that I have added that I have personally found useful. The people I follow, the courses I have taken in the past 2-3 years, and the blogs that I have really liked on philosophy of using AI for learning as well as building. So the resources I have shared on the group, and please join and feel free to build and share.
So if you have any quick questions for Aditya, then feel free to shoot them. And then what we will do is, we'll end the session officially, and then Aditya and his team, they are stand outside, and if wants to make their own app and help from Aditya and his group, guys, they are going to be available. Yeah. Right. So we'll show you. So who all are in his group? Can you guys just show your hands? Just stand up and show your hands. Yeah. So these. Oh, sorry. You have questions, or you are in Aditya's group?
Okay.
No, that's a different ball game. These are the people who will help you. By all means, you interact with them. Okay. So identify them. They will be standing outside. So we'll first finish the question answer thing, and then we will go to that. Yeah. So questions, anybody? Yeah. Go on. This one.
Good afternoon. Build apps using Gemini Canvas. How do you pressure test them using various inputs? Because you do not know what input the person who is going to use that app might give. So how do you pressure test them and ensure that it gives appropriate outputs for as inputs?
So Gemini Canvas is a sandbox environment where you external data connection is a bit tricky. Although my sister has connected with Excel and she saves the data somehow. But what I do is, I only do quick prototyping and concept exploration in Gemini Canvas or Claude artifacts. Once the workflow is structured, then I use fast HTML and build it myself using some AI assisted coding platform like Solvit or Cursor or Claude Code. So different AI tools will have different limitations that once you start playing with them, you will understand. And you can use other tools for building pressure testing and building robust, reliable apps.
Anybody else?
Are there any properties criteria
Can you elaborate?
Hence, like, let's say if you develop an app, you, like does or alpha reserve the right also circulate the app if they.
I don't think so. It's private, although like they might, but like it's just quick prototype. So even if someone else copy, it doesn't matter. It's just 15-20 minutes.
Answer that question on his behalf because I'm the guy.
You are the chair.
I'm the chair and the policy guy. Yeah. So there is a lot of debate on this particular thing. I develop an AI, some tool which has commercial value using AI, then who exactly has the that. And as of find it at the organizational level. So for example, I said that way that if AI is helping for doing something, copyright is has developed the thing, who has used that AI, the AI person. Obviously, the AI companies have a different take on it, and when they have a take and when they do the corresponding, that point works. As of this went to the idea.
If we look at a kind slightly analog, photographers sharing their Instagram, let's say. Copyright is reserved with the photographers, but Instagram also reserves the right to circulate the can benefit from it if they see some point to it,
That
and
is
then
something
you
that
cannot
Instagram
object
has
to it.
explicitly written. To the best of my knowledge, the LLM providers have not yet done any such thing. If they do, when they do, then that's when models will.
Another point I would like to ask, like I'm churning like every single app like every 30 minutes, so it doesn't matter how many, and like it's not a static thing. I'm iteratively improving it.
Aditya, at your level it may not be, but suppose tomorrow one of your app becomes a crore earning app.
Yeah.
Then it might.
So
is what I think he's talking about.
Another topic is like in a business, distribution, relationships, and domain expertise also play a important role.
True.
Apart from it.
But
So,
that is why this is a slightly thorny question with proper answer as of this. Anybody else? Okay. So if that be the case, we'll break the session at the moment. People who are on Zoom, you are also going to help them in case they have any issues, right?
A bit later, like we can ask them to join the WhatsApp group and then we can help them over there.
Yeah, so people on Zoom, please join the WhatsApp group, and if you have any queries regarding your builds, put it on WhatsApp. Aditya's group will answer it there. But here, person, Aditya and his group will be standing outside. They'll be helping out during the lunch, and everybody else we are going to join at 2 o'clock and start the post. Thank you very much. See you at 2 o'clock.
So one request for all of you, like there is this slight barrier in like building your first project. So that's why like just get started. People are there here to help. Build something very quick. It will just take 5 to 10 minutes and see how much capability or power you can unlock starting with this simple prototype. Thank you.
So I think some people who are in here where came as spot registrants. So we are opening that thing again. So if you want to join this and get a certificate, then do the spot registration one more time. And people who are already registered and have came in late and therefore did not sign on the registration, can please again go and sign. If you have already signed in the morning, it's perfectly fine. You can go and have your. Thank you. back to post lunch at IISER. The first half of this have talks, and the first from our mathematics department. Swami did his MS IISc, followed it talks in Netherlands. Currently, he is an of mathematics and data, and he works in the fields of stochastic control and India.
Thank you very much. Without further delay, start my slides. So here I'd like to talk about applications of machine learning in option pricing. So before that, I understand that some students, for the first time you're hearing about something about option. Option is a financial contract. So I'd like to present what we mean by option, and why should go hard to the fair price of option, and what are the challenges and what are the proposed. First, we all know that the market, financial market does have lots of risky assets. Prices keep moving over time in unpredictable manner. So here, this is one just illustration. You can see one, blue curve which is up and down. That is just, a cartoonish representation of how stock market possibly the prices go up and down. And here we see at certain region, the oscillations of the return is less. On other places, oscillation. So, so those are the areas, those are the features are very important for investors. So we even name, we call this volatility. Okay, volatility when oscillation, the return is less, and we say when oscillation. And volatility is something hidden. So here indeed, this red curve shows the levels of volatility. Here it is the lowest in, and here these on both sides is the volatility higher. So this is a hidden factor. So that hidden factor, if one quantifies it, that really helps to quantify the uncertainty, right? That is okay, right? So next we talk about what we mean by option. Here we start with one very simple example. This example here, so you can see on this plot simulation of stocks, movement. There's a 50 ahead, right? And 50 number of possible price paths are, right? And imagine that are, this is the time axis, horizontal axis, time axis, and present stock price is just this value, and then it is all about speculation. Stock price can move in direction, time, and then after 15 weeks, maybe this is the place where all these 50 paths are hitting somewhere, right? And then this blue histogram, which is rotated this way to makes more sense about this of the empirical distribution of the stock price at the final time. Okay. On the other hand, this black line is a particular level of a price. So we call here strike price. So here we are talking about so like position of the black line that we call strike price, and what we are talking about an option. Option is a contract which is a random payoff, and the random payoff amount here for this example nothing but maximum of 0 and S minus. So what does it mean? The meaning is very simple, that if the stock price at time capital T above this black line, that is above, so that much money is received by the holder of that contract. However, largely it goes below, then the holder, the person who is having the contract, no money. So basically, how much the person can receive at the end of 15 is uncertain. But there are some possibilities of positive, and now at times you are, willing to have that. But get that contract, you must pay the person selling you the contract. So how much money are you going to? If you think carefully, you can imagine that this somewhat, equals the of some insurance or maybe warranties. Some random claim happens from the perspective of the manufacturer, and also similar kind of things. How much money the manufacturer should charge the customer. So now let us look at what does this graph offer. Say this part is basically the condition of this random payoff is positive. That is okay. So now we are going to ask questions. What is the price of the contract? That means at time 0, when you do not know what is going to happen in, how much are you going to pay? How much are you ready to pay to the issuer to possess that? Like lottery kind, that can give some positive benefit, but you may not give up, right? So this kind of contract sounds little convoluted, complicated, but actually they're highly traded. Actually, if you look at the data, if you searching percent of derivative volume happens in just one example of it. But so like not only 50% is like percent something more. That time I saw that, but time it is just then market such contracts are highly traded. However, it is not something this. I mean, of course, the market is happening times after, but the existence of such contracts called options are there 100 years back also. So we all understand now the question. Question is that how much the holder should pay to the issuer at time 0. If for an asset, worth is something this at time capital. Certain and comma 0 and maximum money is not. Okay. So the question is that how. Then another question is that the issuer how would that issuer manage? That is also one fascinating. Hedging. Okay. So now let's try to understand what we can infer from just this. We can infer a lot of things. For example, my initial starting point was not below the black line but above, then there will be higher chance that this line will be fall above this. Basically, the value worth of that contract should be more if this stock price was larger. On the other hand, even here also, if my time to maturity, this length was much shorter, chance of going above is less. Worth is that means time to maturity. Also, worth of this contract should be larger. Understand. So basically now, price of option, that question price of option is nothing but finding out a surface or to function of at least two. One is time to maturity, moneyness. All this came out of the money because most of the does not give you. And in the money, starting point is here, and if it happens to be that is starting from the black line here. Fine. Okay, so we realize that present value of the option from OT ITM or okay, so understood. And then the plot graph etc. is something want for precise values. So here, I mean, if you plot this way, the stock price on the horizontal axis, price of the contract here on the vertical axis, then we are going to get as S is on the right hand side of K, the price of contract will be larger. As stock price is smaller than K, the stock price smaller, etc. And then then we also see that time to maturity is larger from green to purple. I will get that the kind of things we understand. But these are all from the reasoning, not from actual values. We are interested in actual values. The family, so basically like surface, we are looking for a surface, unknown surface. And then as also the strike price varies because market, but that for a asset multiple. So as strike prices varies, you will have multiple different. Basically, you have family of surface, and this family depends also on some unknown statistical properties of the stock return. It also depends on the volatility I started with. It also depends on that. The plot what I have shown here, volatility factor was as 20. So have different type of chances. So basically, it's like family of surface unknown that you would like to find out, and volatility is unknown completely, but you have to find out the challenge. So this challenge was taken first, I mean, as document goes, 1900. In a PhD thesis by this, his Achilles, under famous mathematician Poincare, and there he proposed one way, and for that he actually had to develop mathematics, and then it much original, too original to be accepted. Suffered a lot in his career. So I do not have time to of it. But if you have scope, you start with nice biography of. So stock price, he model Brownian motion shift, and then later on, 5 years later, Brownian motion mathematical, and basically for a long time people that was the first occurrence. Okay, so but anyway, so his model was the first proposed model, so he failed to capture some positivity of stock price of that. But much later in 1965, in the work of Samuelson, put that Brownian motion better model for modeling stock price move, and then later on in 1970 there was one publication by joint authors Black and Schultz, and then they worked on finding out fair price of options by considering that stock price. Okay, and then that work was very as a made 1990. Okay, so now let us see. So this is like I mean, I did not talk anything about anything. I just talked about the challenges about. So on those solutions, I have assumed this volatility factor is and is okay. That is fair enough. I mean, for every mathematical model is like that. parameter like this, and then somehow you take this as a separate problem, find out the parameter value, and then you plug into the. Okay, so here the problem that solution, some problems were there that was constant or time banks into other assumption as realistic. But there doesn't matter. There are many different other research that approach and then extended the results for stochastic models, sum diffusion models, and combination of long history, thousands of find fair price flexibility market model. Now, the place, I mean, that why machine learning here we understand that the fair price of an option contract depends on the current anticipation of future, how it not like that, but most out like uncertain. Then so this is something not only anticipated success or failure pricing tied with success in capturing this, of course challenging. So often the simplified assumptions in theory models do not match that happen to peculiar back shows. On the other hand, there are of course some sophisticated models, advanced models. There are many of parameters, but those challenging. You have some that are continuous option price. Those are the things. So business reasons, it is okay at alternative adoption of data-driven approach. So because now that is possible there are competition can do now, right? Have statistical learning technique can do that. So quickly I talk about some in this in 1993 I found this first first network models for ST, but he did 1%, one single that I mean basically the effort was to replicate, not actually beyond the black. On the timeline, Hutchinson's work is also contribute that direction. So it's called non-parametric approach to pricing. Say non-parametric, as that is a common term. Statistics, Black-Scholes parametric, dynamics parametric, parameters. But here in the non-parametric parameter. Okay, so few other works like pricing and works and there are also hundreds of papers. I just picked up landmark and another is 9 option pricing. Okay, so so now in this context, I will briefly talk about now. I'll just talk about that what my research last few years. One work I have done with one data-driven option pricing. Here for the first time, what we propose that can devise a machine model, not then you do not need to restrict it only that particular. That model becomes that another asset for which you have the option prices. M-trained model kind of have to address that question. Have promise where it works, where it doesn't. So, so I'll say just look at this some model assumption that mathematically we had to address arbitrary then stock price dynamics and either asset or Markov or it can be augmented. These are the standard assumptions which are valid for all theoretical that I have. And then I would like to add this conclusion part of this that your left hand side and right hand side looks quite similar. Left hand side I have phi1 function, right hand side phi2 function. Phi1 is size of this one IBM's and phi2 is possibly dances different options to assets, but still you can have some relation. That means one that you is anyway. So this is the main idea, but of course there are many challenges. So here, I mean, there's no. It's not possible to talk about algorithm without talking about target. The target here is that option price divided by the stock price, and then is in feature moneyness, time to maturity, bank rate, and one array of order statistics. Why? Because fluctuate dynamics uncertain, right? And how to capture it as much as okay. So these are the the things we have proved for the model, and we have one graphical illustration. The band is the band, and the red one is actual. What actual is not exact option is hard to, but given the option price, finding out that volatility, that is enough. So this red line is that what is actual value market and what is so some accuracy there. Some accuracy. Okay, fine, but this is only the good part because it is everything. But there is some bad part. Every scientific that it not work some. It did not work. Put attention. Why it did not? A better scope and all that challenge. Also. So here during that we're talking about options one, and then red one is actual and the band you see. Not do, and we started understanding, started asking the why, right? And then what we realized, time do I stop now. 1 minute. And then we realize that, some expression that, yeah, I mean, whenever the test data having statistically similar behavior, something like part is like that, and on both sides the error is lot of error. So then what came very recently last year, market approach, finance, another past student. Here we have actually so I'm not so running out of time. I will not talk anything. I'll just the last slide. Here we talked about two different data, typical and atypical. And what we see that two different methods earlier. So then for typical data, the error is large for the AD. That means, but it went very well for atypical. And then we propose where we merge together to convince appropriate. And there we that is the one short story of some machine learning.
Just slightly out of time. Questions? Okay. If not, we'll thank. So, our Dr. department is an particle of the CNS collaboration Large Hadron Collider. Searches for particles beyond also work developing in strategies data campus sort of.
Okay, so let's get to machine learning in collider physics. The collider physics is a narrower subset of particle physics. And the idea is that first I need to outline what particle physics means. So the broad aims of particle physics are to answer two questions. Take stuff and you start breaking it apart, keep doing that over and over. Ultimately, when do you get to something that is indivisible? So we are aware of this idea, right? Like atoms are made of stuff and then just has protons and neutrons. You can break apart a proton. Where does it stop? That is question number one. What are these indivisible particles? And the second question is, how do these indivisible particles communicate with each other? What are the fundamental forces that exist in our universe? These are the two questions that particle physics tries to answer. Now, as Sudhir said, I'm an experimental particle physicist. And so this is my scandalously brief summary of what we do. We collide protons with protons. That's why it's collider physics. We study this particular collision. What comes out, you take a picture of it. And the thing is, you repeat this a few billion times, which means that you have very, very large data sets. What you can do with this is that this helps you learn about the existing particles that exist in our universe, some of which are indivisible, some of which may not be. And It also helps you find new particles. Now, this is the introduction to what particle physics. This is the one picture that I didn't make in this talk. Got this from the internet in the old-fashioned way, in the sense that I didn't ask ChatGPT to make me a figure. So, what is the point? The idea is that for us, AI or machine learning are tools. They are tools meant to answer the specific questions that we outlined before. Of course, there are going to build those tools. In my head, sometimes I tend to think as, if I'm a painter and I'm going to use different kinds of colors, there are going to be experts who make those colors, right? And then they care about what is the right way to get a color. It should represent the color. It should have longevity. It should not dry up in my box. That's what the person who makes the tool does. On the other hand, the painter just uses it. So all of these beautiful, fancy machine learning, they are users of it. And I want to give an illustration how we go about using it to sort of build a story. So we're going to try to do this a little interactively. I'm going to talk about sort of ideas and then go back to how we would use them in collider physics. The ideas, these are 3 ways machine learning algorithms can be used by us. There's classification, there is pattern recognition, and then there is anomaly finding. And as you will find with a lot of these things, there is significant overlap amongst different things. They don't necessarily fall into neat little categories. So what I mean by classification is you have 2 or 3 or 4 of something, and you have some sort of an algorithm or a black box that answers the question for you, is this A or B? Or is this C or D? Or is this A or B or C or D? That's classification. Pattern recognition is you look at a bunch of data and this algorithm is going to tell you, is there some underlying rule to this data? Is there some structure in it that I am not able to see, or I don't have the first principles theory? The last one, which is anomaly finding, so that is that again, given a data set, is there anything odd in this data set or not? That's kind of easy to sometimes not get. Imagine that if you are sort of let loose on a farm and somebody asks you, go to this farm and see if you see anything odd there, right? Now, if you go to a farm and you find like a tiger there, that's going to be odd. It's not a zoo. So that's what I mean by anomaly finding, something that just happens to be anomalous where it is. Okay, so let's do this together. First thing is, are all of the 6 figures reasonably visible? Yes? All right. So now, the left column is 3 examples of case A. The right column is 3 examples of case B. Okay, so you have 2 different things and you have 3 examples of both of them. Now you are the neurons, right? And so you are going to train yourself, or I am going to train you. I'm going to give you like 5 seconds to maybe stare at them. You will start to notice things. You don't have to share them, but you can keep them in with you. Okay, you've had a reasonable chance to look at what is there. You understand the premise. This is one class, this is another class, and we have these examples. All right, so now the question that comes up is, armed with this data that you have been trained on, let us try to answer the question. Where is the pointer? Here. This one, is it A or B? And this one, is it A or B? So maybe let's start with the top one. What do you think? It seems like it is B. What about the bottom one? Are you sure? Are you sure? Okay, you can be sure. You can be unsure, that's okay. What makes you say that? You saw 3 examples of something, right? And do you know what this is? Do you know what, did I even say that it's a plot? It's just some 3 figures. Did you see, did I explain what it is? Do you think it's collider physics? Doesn't matter, right? But you are able to say whether it is, the answers are right by the way. The top one is B, the bottom one is A. But you did this really fast. What did you do? If you decide to go back, what did you do? You looked at these 3 things, you noticed some features. What was the feature that makes you think that is, someone tell me, what was the feature that makes you think the top one is B? Yeah, there's a bunch of stuff spread out, right? It's not all packed together, which is what A sort of seems to be. This is an example. Actually, this is literally what neural networks do. They don't really care about what you're showing them, but they learn the patterns. That is what we just did. So this is an example of a classification task. Let's quickly also look at a pattern recognition task. Now here I need to set up the problem just a little bit, so bear with me. Imagine that you have a series of these concentric detectors, right? So you have a circle and then a bigger circle and a bigger circle and so on, all the way out. If I have a charge particle, and that charge particle sort of starts in the middle at the origin and then shoots outward. As it shoots outward, it's going to interact with some place along this concentric layer, right? Around this circle, it will intersect somewhere. Each of those intersection points is shown in this cyan color. Also, I'm a little colorblind, so I don't know, green, cyan, whatever you would call it. So that's the data that you have. You have only these intersection points, and the idea is that can we build the right trajectory from just looking at these points? So here is an example. In this particular case, there are 16 points because there are 16 concentric detectors. So now, what do you think? If I gave you this data and I asked you that can you map out the path that the particle took? Do you think you would be able to do this? Yes? No, didn't have lunch? Yes or no? Yes. How many trajectories do you see in them? How many distinct trajectories are there in each figure? Yeah. 3? You're allowed to speak. You can speak. 3, right? That is easy. I look at it, okay, there are 3. We also know that I told you that they start from the origin, which means that in each of these cases, oops, where is this? Here. Each of these cases, they start from the origin and they sort of spread outward. Good. So this is an example where we recognize the pattern. The trick is, why are human beings not doing this all the time? It is, what if the data actually looks like this? Instead of 3, what if there are 100? That's actually what these two examples are. There are 100 such particles going outward. At this point, for me, certainly it is very difficult to match or make a trajectory out. It turns out that given enough examples, a dumb machine learning algorithm can actually do this a lot better than we can do. So this is one example of pattern recognition. Along the same vein, so using the same thing, let's look at a different example. Now here's another piece of information. The way these trajectories behave is that if I have a higher momentum track or a higher energy track, it tends to be straight. And if I have a lower momentum or a lower energy track, it tends to curve more. So those of you who know some physics, you know that this is because of the magnetic field and how charged particles interact in the magnetic field. But the only thing that we need to worry about is how curved something is or how straight it is. Now our job is that, given some examples, are we able to look at a figure and judge, does any of these have a high momentum track or not? Right? Now it looks very suggestive. If I stare at this, certainly here, this is the one that sort of looks straight. If I look out here, I also see something that is straight. Nothing really straight here, but then maybe this is straight enough. So, of course, without quantification, there are no right answers here. You have to quantify how straight is straight and how curved is curved and what are you actually looking for. But this would be an example of where you did some pattern recognition and then you classified. You look at these 4 things, recognize a pattern, and then tell me, does it belong to the class that has a high momentum track or not? Okay. The third thing that we were going to talk about is anomaly finding. Okay? So now, what I'm showing you is a table. The table has 13 rows, 1, 3. Each of these rows represents some particle. Okay? In each row, I am giving you the energy and the momentum of the particle. Momentum is a vector, so it has 3 numbers, x, y, and z. So that is px, py, pz. This is your set of numbers. And you have several such rows. The question that we are going to ask is, if I give you this on a piece of paper, are there any anomalous rows? Is any row an odd one out? Now this is also an exercise that we can do together. So I don't know, throw out some ideas. You can look at it. You can try to notice patterns. Third one from the bottom, and the rule would be that all of the 3 are negative. All of the momenta are negative. Okay, that's one possibility. One, two, three, 4. No, but there's a 6 also, no? Oh, that's the lower one. Yeah, and then there's a 7. True, true, true. So now we see what the issue is, right? there's no rule per se. It's in some sense what you notice the pattern and you start to do these things. Now, one of the approaches that I may take given this is that I want to find something that is odd that you could plot. So what I'm going to do is I'm going to plot, say, the energy, and I'm going to plot the PZ, the Z component of the momentum. So here are two graphs. The top one is showing E, the bottom one is showing PZ. It's a histogram, so the y-axis is counts, so it integrates to 13 because we have 13. And if you look at this, nothing really stands out, right? I mean, it looks okay, something. Yes, or something is standing out. I mean, there are heights, one of them is a little higher than the others, but nothing really anomalous to the eye. Here's the fun part. Suppose now I take these numbers and I invent a function. This function is going to be square root of energy squared minus px square minus py square minus pz square. So this is my function. If I now calculate this function and add that as another column, now it is very, very apparent that two of the rows have distinctly different values than the other ones, and that's unambiguous to all of us. Now again, those of you who are physicists may understand that what this function is. Given a 4 vector, if you do E square minus P square, you get the mass of the particle. So fine, what we've seen is that there are a bunch of particles with a mass of 105 and 2 particles with a mass of 0.5. I mean, it's the same particle. But here's the point. What happens if you don't know this function to plot? This is a really, really weird function, right? It's some square root of something. Arbitrarily, given a sheet of numbers, there's no reason for you to come up with a function that's going to give you this thing very cleanly. This is where a machine learning algorithm, which is sort of a multi-fit, helps. Okay, so now what are we going to do? I don't know, how am I doing on time? Reasonable. So, we are going to put all of this together. The 3 things that we have: classification, pattern recognition, and anomaly finding. And I'm going to try to tell you how I will use it in my research. So, imagine that we are going to search for some new particle. I have some theory friends. I was going to say I have a lot of theory friends. I have some theory friends. And one of them proposes that there exists in our universe a new particle called E, capital E. Okay? The way this particle is produced in these LHC collisions is it is produced with its antiparticle. So the way I produce this is that I produce a EE bar, and this EE bar happened to decay to 3 particles which are called leptons. So these leptons are electrons and muons. So the Greek letter mu is the muon and E for electron, which means that if I'm going to get 3 of these, there are 4 possible combinations that are there. Either all 3 are E, or there is 1 mu, or there are 2 mu, or all 3 are mu. So that's an exhaustive list of all possibilities. What I'm going to try to do is that I have a collision in my detector, and I want to see if the collision has any evidence of this particle E being produced. Now here is the problem. Don't worry about the number 100 inverse femtobonds, but in some amount of data, you expect to see 10,000 such things where EE bar was produced, right? The number is 10,000, which is fairly generous and large. The problem is, from the standard model, from the stuff that we already know, we are going to get about 10 million such events where I'll have 3 leptons. So now my goalpost has changed. I am no longer talking about a single collision. I am saying, given a set of 10 million plus 10,000, how am I supposed to extract the 10,000 that really matter to me? So this is where I'm going to use the 3 steps that I have. So how do we actually do this? This is an example of the CMS detector. So it's a cylindrical detector. The collision happens right in the center. And what you see here is that several particles have come out. Each of these blue line, the yellow lines or the red line going out are particles. The 2 red lines in this particular case happen to be 2 muons. That's how it physically looks in my detector. Of course, this is a sort of a large picture, and actually what's coming out is electronic signals, which you have to then tell what is what. For our purposes of our talk, let us simplify this graphically. Pictorially, I'm going to represent an electron by this shape. So this is an electron, and this is a muon. Remember that what my detector is seeing is an electronic signal. So it's quite possible that I'm going to get an electronic signal that looks like an electron but isn't actually an electron. So for example, if I take this shape here, well, it's kind of like an electron. It isn't, but it looks like one. Same thing on the right hand side. This is not a muon, but it kind of looks like one. So the first use that we're going to do of our classification is to be able to tell what is an electron and what is not an electron. What is an imposter? What is trying to fake an electron? This would be step one. Okay, now we want to look for this particle E, and remember the particle EE bar is going to give me 3 leptons. So a particular collision is going to look like this. I'm going to have the proton-proton collide and 3 things are going to come out. In this case, I have 2 electrons coming out and 1 muon come out. Okay? So that's what the picture means. Now remember, we have many such collisions. So this is what we have in hand. Now the question becomes that, okay, if you have so many of these and they come in all varieties, 3 muons, 2 muons, 1 electron, 2 electrons, 1 muon, how do we identify the 10,000 events of EE bar from these 10 million known background? This is where we use classification and this is where we use anomaly finding. The concrete way in which you would do this is what Anindya was also saying. It depends on the properties. The easiest way to think about this is if you're thinking of telling 2 things apart, how would you tell a cat apart from a dog? This is the favorite example that we like to give for classification. Well, you can tell a cat apart from a dog typically by some properties that cats and dogs have. For example, you could probably tell how long its whiskers are. Can it arch its back? Does it have 9 lives? Or you could also say silly things like, let me count the number of legs. That would be a bad thing to do because if everything is going well, both the cat and dog have 4 legs each. So that's not a good way to tell them apart. But the whiskers, colors, these other things are good ways to tell them apart, which is where the physicists come in. It's not just running a classification tool, it is to know what are those features, what are the properties that the EE bar has or the standard model thing has that allows you to tell the difference between these things. So that's where I'm going to stop for today. I'm going to summarize. So this CMS experiment has many billions of these collisions already saved. All of the data we have and we're collecting more. Depending on what you're interested in, you want to identify some vanishing subset of this. So here at IISER, the sort of objects that we look for are called vector-like leptons or sometimes other things like leptoquarks. We use a variety of machine learning techniques for this. I sort of mentioned 3 of them, but I didn't talk about generative AI, which is how most of you would usually interact with AI. Like ChatGPT is a generative model. Those are also used, but the thing what Sutirth was saying this morning, and I already had the slide so I kept it in, this is what we don't do. We do not outsource our thinking to AI. Some doing is okay, right? The thinking is the thing that we want to do, and so you reserve that right for yourself. So I'm going to stop here, and I'm happy to take questions. Thank you.
So because we also have people online, unless you speak in the mic, they can't hear the question. Hence.
So first of all, thanks for beautifully explaining it and making it so interesting, particle physics wise and also application of how to do that.
Thank you.
Now I want to know is, these are the experiments and so much of data is collected. So is there any plan or are there any further experiments done? And is there an angle of purely science and experimentation study or practical uses of this particular experiment?
So no, to sort of take a slightly extremist view, no, this isn't done from a desire to do application. A lot of it is let's just learn something new. Of course, what happens is over a period of years, what you learn, like back when the electron was discovered 300 years ago, there was no electronics. Then of course, now that the electron is there, you invent electronics. That's how it goes. Nevertheless, there are actual sort of side quests that happen. For example, the ability to share large amounts of data, development of radiation therapy, how stuff can be made radiation hard so that if you send something on a spacecraft, how is it going to survive there? So these are things that sort of fall out of the research that we would do here.
Just a small follow-up to it.
Is there any public participation, or can people join the experimentation?
So a lot of data now, we are also moving to this open data model where a significant amount of data is in the public domain. One can get trained on using it. There are examples. It usually helps if a set of public people or students work with somebody who knows a little bit more. That way the progress is faster. But I've actually had students do stuff on their own and send me stuff, and it's super impressive.
That's the thing with AI.
Yeah, I know, exactly.
Changes the bar.
They manage to get stuff done.
Yeah.
Thanks a lot.
Thanks. Took me back 50 years ago when I used to have friends who did this kind of thing, or at least particle physics. You said you also use generative AI, which you're not talking about today. Why do you use it, and what difference does it make?
So to learn a lot of things, sometimes you need simulation of the detector and whatnot. And making detailed simulation of the actual detector is compute intensive. So sometimes it's easier to do generative AI to just generate the subset of information that you need. That's the largest use.
Anybody else? Anything from the Zoom side? No. Okay. So, yeah, thanks, Saurabh. Yeah. This is not showing up. It's not showing up. Is Professor G. Nagarjuna. Professor Nagarjuna is a visiting faculty in the Department of Science Education at IISER Pune, and he was formerly a professor at the Homi Bhabha Center for Science Education, TIFR, Mumbai. A philosopher of science and cognition, he studies the biological, cognitive, cultural, and technological conditions that make STEM practices, framed by the guiding question, what makes STEM practices possible? He is also an advocate of digital freedom, promoting open standards and protocols, and the use of free and open source software in place of opaque proprietary platforms that constrain users' freedom. He wrote it, I didn't. So, Professor Nag.
Yeah, thank you. So, we have been hearing a lot of our colleagues. They are scientists. Science. They do research. And I am, in that sense, do not completely belong to that thing. I am margins of the practice that happens at I. And of course, that was also true when I was working at TIFR as well. I was always on the margin because I'm trained as a philosopher, working on the problems of science education. So I'll just start with one critic, because that is what normally we hear from a large number of critics, and one of the persons who is also my fan. I mean, I'm a big fan of the work that happens at Santa Fe Institute. And David Cracker, who is of course the current director, I borrowed this slide from him, which actually says, of course, that Philip Anderson's quote, that emergence can be defined as more different, because as multiple things get into the system, suddenly something else comes up. That's what we normally call as. And then the other way of defining, for example, what intelligence is, say that less is more, in the sense that particularly the kind of science that we do, like physicists come out with a nice equation, a simple one being F equals ma, and you can do a lot of things with that. So it is in that sense, one single function or an expression, and you do a lot of things using that. So that's what we mean by less is more. And then he very jokingly criticizes LLMs, because LLMs are more is more, because they eat a lot of data and they do a lot of halla, And so that's the sense in which he was talking about more is more. And of course, the idea that he is trying to say is that the emergent intelligence is the kind of definition that he is trying to talk about, because he's a big fan of emergence. And he says that less is different. So that was the context in which this is the thing. I mean, there are certain things that you can agree with, but I think that's not a good interpretation. And I'm just using two examples here of how it's not just LLMs, that we also consume a lot of data. For example, Likon, who left Meta recently, of course, one of the people who won a Turing Award, a 4-year-old consumes more experience in life than what the current LLMs are actually consuming. And of course, he's not talking about the data in terms of the text feeding or images and things like that, but he's talking about actual experience of a 4-year-old, because children explore the world with a lot of enthusiasm and a lot of motivation. And there's a lot of play, there's a lot of passion, and of course, there's a lot of cry as well in the whole process of submitting to our environment. But we should not also forget the other important thing, that we as natural systems, and the kind of data and experience that has actually been part of us, not directly, but through the seeds that we got, the experience that we consumed for 4 billion years of evolution. Of course, it's a big assumption that we're making, but then we can't ignore that, because the way we are today, the kind of things that we do, we cannot say that they are just because of what is fed during our lifetime, because a lot of things actually come out there. So I would be using this particular lens again and again during my talk, and trying to see what kind of educational implications one can draw from this particular lens, schematic and stochastic lens. So, so the left-hand side, you see the classic AI, which is what I call the schematic AI, where people have put together a lot of knowledge base, which is curated. So you put a lot of concepts, you define the relations, what are the predicates, what are the rules, and what are the premises, and you put all the premises and things like that, and then you apply logic and reasoning on top of that, and you query in a very SQL kind of manner, not with a natural language, and try to get some interesting results out of it. It's been successful in many domains, particularly the experts' knowledge, like doctors and very specialized engineers, things like that. But it's not very good with related to common knowledge. On the other hand, the current model is largely, of course, that's simply a caricature of stochastic things. And what goes on the left-hand side is expert system, logic, and reasoning with a lot of data. And on the other side, you have stochastic mathematics. There's a reason why I want to call it just the mathematics. I'll just explain it in a little while. And that's a kind of generative model that we are largely using right now. So this is basically a small caricature of how the model basically is supposed to be working, in the sense that most of the data that gets into these machines, and it gets converted internally in an implicit way in a model of this kind. And so what actually goes there, of course, a lot of things, a lot of linear algebra goes there. There's a lot of mathematics, as you can see, statistics and probability. But you also have some physics there, dynamical systems and nonlinear systems as well. And a lot of logic and statistics again, like Bayesian inference, Markov blankets, neural networks. And then you have RNNs and CNNs and all kinds of networks, etc., go in there. And this is largely, of course, you can call it as computer science. But then, at the very core, it's a lot of mathematics and logic and physics, which is actually generating stochastic patterns. So, but because the mathematics is schematic, okay, I wanted to say this point, that schematically re-represented stochastic operations are becoming the seed for most of the things that we're doing today in terms of AI. And of course, as a person working in philosophy and cognitive science, I would like to see if this is possibly also true about the foundation for learning sciences as well. So what are the implications of this lens to higher education and research? Of course, a very sketchy kind of a presentation, which will not be possibly having a lot of time to discuss. But so this is what Emily Bender, for example, talked about as a description of what LLMs do. So highly fluent stochastic parrots with occasional brilliance. And because they give you the feeling of it seems right, and then you end up concluding that it is right. You know, there's a kind of a warning that Emily is pointing out here. And then, who are we? Of course, the professors, and also maybe even some of us who are already doing it. If you follow that kind of a model, and if you agree that there is this element of stochasticity already within us because we're all natural biological creatures. So I would say a highly fluent stochastic parrot with occasional brilliance running out, but it's operating at room temperature, eating roti, dal, or whatever food you eat, and drinking an occasional dose of caffeine or some other poison. Well, essentially, the idea here is to say that the natural agent is, of course, operating at room temperature, whereas all these, whether it is ChatGPT, Gemini, and things like that, as you know, all of you know that it's like a big, large institutions running at too much of natural, almost like a natural disaster. And of course, the part that I put on the brackets is largely a kind of a speculation, in the sense that, most likely the bodies that we are carrying are largely some kind of either a reservoir computer or a recurrent neural networks running at, of course, at tool body. Now, this is a provoking statement to talk about von Neumann. And of course, this particular image was generated today morning using this following prompt. I said, generate an image of von Neumann, who was renowned for his rapid, intense, often chaotic blackboard work and things like that. He keeps on erasing something, writes something else, and things like that. So he's well known to be very good in rigorous, formal, symbolic operations. And of course, he did a lot of engineering models as well, because the current computer model that we use is also something that is designed by von Neumann. So, is he a parrot? Is he a schematic parrot or a stochastic parrot? I mean, I'm just using parrot basically to give you an idea that there is some element of a living creature, a living person responding to the whole world, and how are the models actually happening here. So in one sense, one can say, for example, that there is some kind of a, because normally we think that, there's a lot of things are happening with these computers and the way how we are expanding with ChatGPT and things like that. But a lot of negotiation happens between the natural language interface that we use and the tensor or vector represented, multidimensional space that the computers are using on the other side. And that negotiation has to be proper. Otherwise, what you are saying, they won't be able to understand, or what they are going to send back will not be able to. That means there is a kind of a mapping that is happening between natural language and the thing. That means there is a symbolic mapping to what we already know, what we speak, and the kind of computation that is happening inside. And then when we think in terms of the interaction between a professor and a student, or between two professors, we are again negotiating between formal schematic language, and if you are a physicist, like Saurav works with stochastic nature, and he is actually also trying to come out with a mathematical language that models the schematic stochastic nature. So it's in that sense, that kind of negotiation is happening as an experimental physicist. So, of course, we all know that higher education is not so easy. Very few people get into higher education. Most of us are very fortunate to get in here. And one of the important reasons is that stochastic things in the actual life of just experiencing the world and things like that as it happens is not actually going to be very, very difficult. But on the other hand, schematic way of learning knowledge is very, very difficult for various reasons. And one of them, of course, is that it is unnatural. That's why we call it artificial to begin with. And then uses arbitrary symbols. And then also, because the symbols are arbitrary, you have to actually come up with definitions. And some of them, definitions are conceptual in nature, and therefore, which is what gives rigor to what we do in both maths and science. And as Daniel Kahneman calls it, this is slow thinking. So it is in that sense a very difficult, and that is one of the reasons why higher education requires a lot of drill, a lot of practice, a lot of redoing the same thing again and again, and performing a lot of mistakes and learning from those mistakes. So all this happens in a way. So the question, of course, then we'll have to ask is that because of the AI that we have, and it was actually partially true even at the time when we were using search engines, there's no poverty of content. At least now we all agree that there is no poverty of content. Good, bad, ugly, whatever it is, we have a lot of content out there. So don't spend time delivering content or even seeking content from us. And that's a kind of a small prescription that comes from the way how this has been put together, because content, there is no depth of content. And then there is a possibility, but then we have to engage with content, and that's why, and that engagement with content better happens when you actually start creating or writing such content, which is a kind of a model of a philosophy of education, which is normally called constructivism and also constructionism, and which is a kind of an interesting normative stand that comes out of that. So there are two things here. Of course, one is content, the other is context, and also culture, because the culture is something that is in between the context and the content. So one possibility of doing that would be to push students to a context of negotiation. And whether you do it with a live professor or you do it with a kind of an AI agent, it's one and the same thing. For example, you have to think about what question I should ask to both the agents. And it always depends on what question you ask and how you formulate it. The response comes back to it in that sense. And it is in that sense, I'm just trying to call it as, whether it is a prompt engineering or it is a context engineering, they're both the same as far as this particular aspect is concerned. And there is an interesting, very easy to read book by Mitchell Resnick, who was at MIT Media Lab, who is still at MIT Media Lab. And if you have time to read this, this actually sort of gives you, this is not written, this is written prior to the GPT revolution, but still the pedagogical advice that he gives is still very important, even in the current context. So now I want to talk about how I, as a philosopher and a cognitive scientist, actually using AI for my work. So my research problem is slightly introduced already to you, which is the tension between schematic and stochastic modeling of learning and cognition. So trying to see exactly how these two spaces are actually negotiated and how learning space actually comes inside that. So these are all the various groups of people. As you know, you have physics, you have chemistry, you do various subjects, and there is some kind of a normal practice, and there are textbooks available to you. But the area that I'm working in, which is cognitive science, of course has some journals, but also has some textbooks, but then no two textbooks look very similar. So they're always written with a lot of bias, and there is a lot of debates happening between them, as your experimental paradigm is not correct because that is not who human beings are. So their definition of who are we changes completely because of the various patterns that are there. So this is the kind of literature that I read. So there are some overlaps, but then there are also fights between them. And all of them sort of looking at one possibly area like this. So after my retirement, I was here in the sense of reading this kind of literature. So I retired in 21. I joined IISER in 22 as a visiting professor. And today, I can say, because I started using GPT, my collection of my bibliography and the reitations and the notes sort of expanded to something like 600, 700 articles and hundreds of books and things like that, but all of them related to this particular cluster. And that, for example, of course, is an operational advantage that we have, given that we have a nice tool using which you will be able to do it, because there is no depth of content out there. But then what you have, of course, have to do is ask the right questions. You know, that is what I'm talking about, the context engineering. And there is, of course, the kind of prompts that I gave. Of course, I didn't give the prompts to the thing about my research project, which is on action patterns and their role in learning. And so I've given all these kinds of action patterns, the kind of signals that we use, the kind of tools that we use, and the kind of manner in which we work with and things like that. And what happened over a period of time is doing all these kind of queries. Of course, I did not give them the images, but I described those images during my prompt. And then, because I don't read computer science, I have only read this part of robotics and cognitive science that is there called cognitive robotics. Here I am citing one from a very nice textbook by Zuntani. And this is what I sort of discovered for myself. And I spent like 2-3 weeks after this reading about reservoir computing and also RNNs. And it sort of appeared to me like a very interesting operational discovery that I was able to make, because earlier to that, I wasn't actually reading in my philosophy and cognitive science literature anything about RNNs and anything about reservoir computing. So these are some accidental discoveries that you make, and then it stimulates you enormously to get into some new territory. And then, of course, you come back to your own original problem after some time. And my second example is something like this. So I described my problem, because I've been trying to look at the evolutionary origins of how various kinds of action patterns emerge and what is their role in cognition and things like that. And when I did this, I discovered, again, due to the kind of suggestions that I got from the LLMs, of a new concept which I never worked on before. Of course, it is very popular to people who are working in animal behavior and social behavior and things like that. And again, this led me to another new, almost like 20-30 days I was spending entirely on trying to understand exactly what is the role of this thing called discovering site fidelity, and how that actually helps in contributing to it. And I almost wrote a complete chapter later on in my monograph, just expanding on this idea of how it happened. I mean, I was, of course, I would have discovered it otherwise also, but then it would have required me to attend so many conferences, or maybe, reading so many books and things like that. So these are a lot of advantage that we have using. Okay, those are 2 examples that I take from my research examples. How much time do you have? Okay. So this is my other example. So I was a PI at TIFR on a lab like this called the Knowledge Lab. And I did a lot of coding work there. I developed network model. The project started with understanding and modeling knowledge as a network. So I worked with semantic webs, I worked with knowledge representation, and a lot of coding was done, and developed collaborative learning environments and tested it in large number of schools at various scale, of course, to understand exactly how learning happens, and then what kind of support the information technology can offer in performing that. Now, this particular project, and this started after I joined here at IISER, and most of my interactions with AI actually also happened after joining here. So I developed what is called a notebook. Okay, so notebook is not notebook. It's just a pun with the idea. So on the left-hand side, you actually write some text in Markdown, and then it's supposed to give you a graph like that. The idea, of course, here is being that you have natural language, something that looks very close to natural language on one side, and then you convert it into something that is machine usable, like a graph representation on the other side. And without getting into too many details, I just wanted to say that I ended up producing, it's like a full stack application development with 6 agents sitting behind and then querying all of them through protocols and things like that, all happening on, of course, on my laptop here itself. But the entire code, I would say I have written only 2% of the code myself. 98% of the code was generated by ChatGPT, and of course, I have kept the entire prompt context and things like that, because I also wanted to look at how that can be analyzed and things of where it works, where it doesn't work, and things like that. So, of course, as I said, the code is available. Sorry, I think I pushed the wrong button. So this is the GitHub where the code is available if any of you are interested to see about thing, and it has got multiple versions because in each version I was using a different agent, trying to see the differences between how Codex would work, how Gemini would work differently, and how my own model that was locally used using free and open source models which are downloaded from things like DeepSeek and things like that, and what is the difference between all of them. So this is another experience that I had. But what I have now is an application with full coverage of the code. That is, all the unit tests have been written, and it's a functioning application to the extent that that project is actually being developed. It took about like 2.5 months to develop, but still it is a big achievement for me, because if I had to do the same thing when I was at TIFR with the Knowledge Lab, I usually had something like 4 or 5 coders, and then we used to develop this for like years. It could have taken something like 2-3 years with 4 or 5 developers and things like that, which I was single-handedly able to do it on a single machine. So there is a lot of help. But just wanted to say, what is code according to the lens that I told you right now, is that you are converting a natural language into a schematic output, because the code at the end is a schematic output. So on one hand, what is actually happening is these chatbots are actually able to generate a kind of an output that you would be able to consume in both stochastic form, natural language form, as well as the form like mathematical or programming kind of form as well. Of course, I don't think I have time for the live demo, but I will, if any of you are interested, maybe we can go back to it. So last concluding remarks, in terms of course, very quickly drawn remarks like this. In fact, I removed a large number of slides after hearing the accidental speaker in the morning, I listened to him, so therefore I removed a large number of those suggestions, but these are some of the things that I would certainly like to say. So negotiating with schematic and stochastic reality is the essence of being human scientist, with or without AI. So essentially, that with and without AI is actually for me a very important one. And there is no poverty of content, so don't seek content from professors with or without AI. Stay in the context of negotiation by learning to create prompts. That is, prompts here, I mean not just AI prompts, but also asking questions and engaging in discussions and things like that, negotiating. And you cannot challenge AI agents with good prompts unless you have schematic competence. So that's where the higher education institutes provide you with that schematic competence. There is no excuse for not practicing yourself with the symbolic competencies. Thank you.
Any questions for Professor Nagarjuna? Okay. There, one, there, that. Yeah, he is getting.
So generally, in science or research, there is some vocabulary and it means something. And generally, what happens in classrooms is that the professor might have a very different understanding of that. But let's suppose take a word stochastic. A student, when the student hears the word stochastic, a very different mental models fire up when compared to what the professor is thinking. And the professor kinds of assume that you have the kind of the context of that. So like so this creates kind of learning deficits in students. So is there like anything for student like they can like better understand in the class?
Yeah, in fact, historically speaking, you know, when Newton started talking about things like force in a very specific manner, you know, it's defined in a particular manner. It's not the same thing that people were using earlier, like force, impetus, momentum. All of them were used synonymously at that time. So the option is, don't call it force, just call it foo bar or F or something like that, because it is defined symbol. So that's what scientists do, which is that, you know, follow the definitions, don't follow the term at all. So keep the term as if it's just some kind of a symbol, or just replace it with foo, alpha, beta, whatever it is. Understand the relations between them. So that's the lesson from what I gather from science, that, but you are completely right about this, and that's the reason why I said we have to negotiate between these two spaces.
Anything, anyone else? Huh? Yeah, go on.
So there is one question online, on the online session by Vishnath Kale. In context of more is more, can we say it's not more experience but more documentation?
Okay, so that was, of course, in the context, but you know, the more is more is a created joke by David Greco, basically to understand the problem of that kind. But you're right, I mean, you can give another interpretation to that as well. Yes.
Anyone else? Okay, if not, then probably I would like to ask something. So you seemed to say that, you know, prompt engineering is extremely important, and I totally appreciate, you know, the context in which you're saying that, no pun intended. But at the same time, I mean, since we are explicitly talking to students, I think would it also be necessary to emphasize that a prompt is important in terms of, you know, having a good conversation with the AI and a useful, meaningful conversation, that is fine. But at the same time, we also need to the students and ourselves as scientists to develop our domain knowledge such that we are in a position to judge the output of the LLM. And in the absence of that judgment, we are going to be in trouble.
Yeah, so in fact, I completely agree with you. And if you notice, that's precisely what I said in the last one, is that, you know, you can't actually write a good prompt, you know, unless you have a very good understanding of schematic knowledge, which is conceptual knowledge, and also the relations between them. Yeah, but the other important thing is also, you know, the reason I have put that extra qualification with or without AI is particularly because prompt engineering, if you translate it to the kind of interactions that are happening between you and me right now, or between the audience, is all about one agent talking to another agent. I mean, I'm just using you also as an agent because ultimately that's the way how cognitive science deals with all of us as. And so, how do I evoke or elicit your knowledge from my questions? Okay, and that is also for me a prompt engineering in that sense of, you know, developing that ability to, you know, ask good questions or seek feedback to what you have done and be very explicit and to the point. And how would you do that without schematic understanding? So I completely agree with you on your analysis. So therefore, we are together on this point. Yes.
Perfect. Thank you. Okay, so if there are no more questions, we'll break at this point and we'll come back at 4 for the last part of the last session. So we still have tea outside. Please join us, and 4 o'clock we'll be back. settle down, please. So now we are in the last part of the last session. We'll have a talk, an open mic session, and then followed by the director's address. So with us we have our next speaker, Professor M.S. Santhanam, who is a professor of physics at IISER Pune. His research work spans quantum chaos, quantum computing, quantum machine learning, nonlinear and statistical physics. He has held visiting positions at ICTP, Trieste, Italy, and Oxford University, UK, and Max Planck Institute for Complex Systems, Dresden, Germany. His current work is focused on quantum computing and quantum reservoir computing models. He also writes extensively in the media on science and technology policies and issues. So, Santhanam.
Okay. Thanks, Sudhir, for organizing this and for the nice introduction. So today, as the title says, I'll talk about quantum machine learning, and there is a question there, does it help us? I was told by Sudhir that the audience is heterogeneous, so maybe I'll spend a slide or two on like an introductory slide on what is quantum. So as you can see, there are some technical terms, quantum, and then there is machine learning. So as we go ahead, we'll see them. So quantum mechanics, most of you already know, even if not deeply, at least as a framework that is useful for description of atoms, things like electrons, protons, and so on. And what is also known about quantum is that it's very, very counterintuitive. So you have statements like this from none less than Niels Bohr, saying that if you're not shocked by quantum mechanics when you first encounter it, probably you've not understood it. And Feynman is even more straightforward, saying that no one understands quantum mechanics. And that's because it has many of these very counterintuitive ideas, things like superposition. Things can be in superposition of very different states, and it's kind of exaggerated to say that something like a cat can be in a state of both being living as well as being dead at the same time. And this is the video that won't work now because I'm using a PDF file. So one of those, another counterintuitive thing is quantum tunneling. So I don't know if some of you might recognize this scene from Harry Potter movie, where as Harry Potter is looking for this platform number, either 9x38 or something like that in 93x4, sorry. Yeah, so he actually goes and dashes against a pillar and finally finds himself transported to that place, essentially is tunneled into it. So yeah, so these are kind of things which is not just fictional, but actually happens at a quantum realm. And despite all these very, very counterintuitive effects, they have helped us a lot in the last 100 years. So mobile phones, nuclear power, MRI machines, GPS, electronics, lasers, everything has come out of quantum physics. So this is usually called nowadays quantum 1. So starting from 1925 to right now, it's almost a century of quantum physics. And so this is all quantum revolution 1, a kind of 100-year-old story. And currently, many people say that we are into this quantum revolution 2. In quantum revolution 1, we have exploited things like wave-particle duality, maybe uncertainty principle. So we learned a lot about atomic structure and molecular structure, had wonderful solid-state devices, and so on. And in this quantum revolution 2, we'll see more of it, but actually have even more finer control over more delicate quantum phenomena, things like superposition and entanglement. And generally, when one says, one talks of this quantum technology, there are basically 4 pillars to it. Quantum computing is the kind of holy grail, but there are others like quantum communications, sensing, and quantum materials. But for our purposes today, we are going to more say something about quantum machine learning, which is to say that we'll try to use quantum effects to do better machine learning than the existing classical techniques, say something like deep learning methods and so on. So essentially quantum 2 is about using quantum effects to do better computation, better communication, better measurement, sensing and so on. And so there has been a whole lot of headlines about these things already in the newspapers. It would be very hard to miss it. And things that would say that quantum is already brought in so much revolution as to, like for instance, reduce poverty, clean up environment, and take care of all our problems. So many of them are kind of overstated, but nevertheless there is a grain of truth in many of these things. So one should take many of that with a pinch of salt. So essentially the point that I will be talking about is about machine learning and quantum, or here it is overstated as AI and quantum. So I put this question to Chat GPT. What is quantum machine learning promising to us? It gave a reasonable answer, so I decided to keep it as a slide here. So the promise of quantum machine learning is that computers could make certain learning tasks drastically or dramatically faster, more expressive and more efficient. So all this is compared to classical learning techniques. And to do all that, it's going to exploit all these phenomena like superposition and interference. The promise is that it can probably train much faster, maybe one can do with fewer parameters and so on. So in any case, for our purposes now, we need to first understand what does it mean to say something is faster. Does it mean that if I use a faster computer, I'm actually doing something faster at all? Okay. So let's address that question. So typically, this is the question about what is called computational complexity theory. So I am given a very, very watered down version of what it means for our purposes. So for example, if you look at this graph here, on the y-axis is the time taken to solve some problem. You can state any problem and the time taken to solve that problem as a function of size of the input, which is given by capital N. So for example, you consider this maze problem. Everyone must have solved at one time or the other a problem like this. And if you look at this small maze, even while sitting from there, you can easily find the path from the start to the end point. But on the other hand, if I had given you a maze like this, it will, which size is about 20 by 20, it is much, much harder for anyone to solve it. It is going to take at least much longer time than solving this smaller one. To understand it a little better, maybe you can think of cricket as a compute problem. Maybe appropriate given that yesterday India won the Under-19 World Cup and is going to start a campaign today on another World Cup. So for instance, if you think of a T20 match, so 20 plus 20, there are 40 overs, and it takes about 3 hours or about that kind of time to complete it. On the other hand, ODIs will be about 50 plus 50 overs, so 100 overs and about 9 to 10 hours. On the other hand, test match is typically 90 overs per day, so about 450 overs, which goes on to 5 days. So you can see that as you increase the size of the problem, so size of the problem is, let's say here, the number of overs being bowled, the time taken to complete it increases, and it's not a linear increase, okay? It could be non-linear. So thinking about it in a more general manner, there are two possible scenarios here. One, that you can have a situation like this, where the time taken to solve the problem increases as n to the power mu, which means some polynomial in n, and that's not really the worst case scenario. You can hope to solve your problem in reasonable amount of time. On the other hand, the worst case scenario is what is indicated here in red, where the time taken, t, goes as exponential to the power n. So as soon as the problem gets a little bigger, you are actually thinking of time that goes as e to the power n, which is really a large number. And for many cases, the time taken is much larger than even the lifetime of the universe. So that is like a computational physicist nightmare. So things are not going to be solved in reasonable time. So one would call it NP class of problems and so on. So in this class of polynomial time solutions are many practical problems. For instance, matrix diagonalization. You take a large matrix, large n by n matrix, and the time taken to solve it goes as of order n cube. On the other hand, searching an unstructured database, which is like you have, let's say, names of all the people maybe at IISER, and they are not ordered in any particular order, like alphabetical order or anything like that. Then you have an unstructured database, and you are looking for one name in that long list. If you are unlucky, the last one is what you are looking for, so that will take of the order of n queries in some sense to solve that problem. But nevertheless, all these fall in this class of n power mu, so reasonable. You can still, in your own lifetime, hope to solve the problem. The other hand, the more difficult ones are things like this prime factorization. If I give you a number like 15 and ask to tell you, give me the prime factors, it's very easy. Without batting an eyelid, you tell me it's 5 into 3. On the other hand, a large number like what I have written here, if I ask you, like, tell me what is that n1 and n2, which will give me this, it's going to be very hard. And this is so hard that it will take extremely long time to solve the problem. And today, most of our information security actually relies on the hardness of this problem. So this entire RSA crypto system, every time you use this HTTPS, that S in your browser, when you type in the address, stands for security. And it actually implements a version of this RSA crypto system. So all these banking transactions, everything relies on the fact that it's very difficult to solve this prime factorization problem. So the quantum computing got a fillip from the fact that in 1996 there was this Grover's algorithm, which gave an exponential speed up to this searching an unstructured database problem. And almost 2 years earlier to that, in 1994, Shor's algorithm exponentially speeded up the prime factorization problem. So that today the situation is that if we had a big enough quantum computer, we'll be able to we'll be able to solve these problems and maybe even break the crypto systems. That's a kind of worry that's currently working at the back of the minds of many people working in this area. Now, so these are some of the algorithmic, important algorithms which kind of gave boost to quantum computing. But there are a whole lot of machine learning algorithms which had a quantum to it since about, say, 2009 or 2010. Things like algorithms for solving linear systems of equation, or clustering algorithms, or optimization algorithms, and so on. And here is a list of whole lots of algorithms. For instance, least squares fitting, or PCA, that's the principal component analysis, quantum version of PCA, quantum version of support vector machines. So each of this is a well-known algorithm in machine learning, and there are quantum versions of these algorithms. The numbers that you see here, all these order of root n or order of log n, basically they tell you the speed up over the best currently known classical techniques. So each of these, many of them do have exponential speed up over classical techniques. So if you calculated PCA for large data sets, you know how painful, how long it takes, and this one promises much faster solutions. And many of these problems are also the kind of things that have very many industry applications as well. And if you go to this site, you will see a whole lot of description of these kinds of algorithms. And being an area of physics, there are also experimental realizations. I've shown some of them. So most of these algorithms have experimental realizations where they do show that this is just not some fancy mathematics, but actually works in practice. So quantum computing actually promises speed up for many machine learning problems, and there are many such algorithms. I would say more than 100 such algorithms do exist. So I'll just maybe focus in the last maybe 6 or so minutes that I have. I'll just focus only on 2 of those to tell you what it is. And so for example, this is another headline about better machine learning models with quantum computers. And when you say better, it means that something like ChatGPT has a trillion of parameters, and to train them you need huge amount of electricity. And some of the promises that come from quantum machine learning is that not only that you can train better, hopefully you can also reduce the power usage. And so the training is expensive. One of the hopes is that situation will be much better if you are able to realize some of these quantum machine learning algorithms at scale. Okay, so as I said, I'll just focus on 2 of them at a very, very top level. Each of them is a fairly involved and a deep algorithm, so it's not time for me to give a long lecture on that. So for instance, this one of the very well-known ones is this what is called HHL algorithm, named after the authors Harrow, Hasidim, and Seth Lloyd. It's an algorithm to solve what is called a linear system. So linear system is a fancy name for what a small piece of mathematics you must have done in your 10th standard and so on. So you have 2 equations like this and 2 unknowns, x and y. So the question is find x and y. So as a 10th standard level problem, it's very, very easy to do it. You just, maybe even by looking at it, you can give the answer. But on the other hand, typically many partial differential equations that is used in industry and so on, they ultimately reduce to, through their algorithm, you do all kinds of discretization and so on, but finally you reduce it to a linear system, which will have like million such unknowns and a million equations, or even more in the worst case. So maybe every time you fly an aircraft, so someone somewhere has solved such linear systems to make it airworthy. So those are the more difficult ones, and those problems you can't solve by hand the way you do a 2x2 case like this. So in that case, the usual classical algorithm or the complexity, the time taken to solve goes as order n, which is basically the number of unknowns multiplied by what is called the condition number of a matrix, that is that kappa that you see there. HHL algorithm, which is purely a quantum algorithm, promises solution in log n times kappa square, which really is an exponential speed up, much faster than the best classical algorithm known for linear system. And of course, I'll not discuss details like this is, for instance, is a typical quantum circuit that will implement an algorithm. So what you have there are a quantum Fourier transform, some rotation gates, and so on. Okay. But nevertheless, ultimately it boils down to, at a very, very top level, it boils down to matrix vector multiplication, a series of clever matrix vector multiplications. So another problem which I will focus on is this what is called the support vector machine. It's almost like a workhorse of machine learning algorithms. So the problem is simple. So if you have these kinds of data, the data which is blue in color and green in color, the idea is to be able to draw a line so that you can separate the 2 classes, the blues from the greens. Okay? So you maximize the distance between these 2 classes of data sets. And it's a supervised machine learning algorithm, and this is what we want to do. And so typically in the classical sense, you would make it into a quadratic programming problem, but the classical SVM can be solved in polynomial in n and m, where n is the dimension of your feature space and m is the number of training vectors. The quantum SVM again provides solution in logarithm in m and n, which is also an exponentially faster algorithm compared to the best known SVM algorithm. And there are technical details about how it works, but again, I'm going to skip it. So here is the top level view of the difference between a classical and a quantum algorithm. So typically, at a very, very top level, you have some data, you have some machine learning model, and finally you have an output. Hopefully it's a useful output for your purpose. But when you come to quantum machine learning, you have the same data. Data can't be different. You have the same data, but what you need to do in between is encode the data into quantum states, because quantum systems don't understand our classical data that we have. So which means that if data is something like this, B0, B1, B2, B3, some numbers, you need to transform into quantum states. That's like transforming this set of images, all these dogs and cats, into superposition of quantum states. That goes as input to your quantum machine learning model, and then it returns again some quantum states. Once again, you need to reverse that, go from quantum states to classical data, and of course then there is an output which is hopefully useful for our purposes. So in this sense, there can be at a very top level 4 different types. The data can be classical or quantum, or your algorithm can be classical or quantum. But a typical quantum machine learning algorithm is when your data is classical and algorithm is quantum, or when your data is quantum and algorithm is classical. Algorithm is also quantum. And there are all kinds of taxonomy of this QML algorithms. And the applications are very many. As I said, the problems being solved are of great interest in industry. So it can range from drug design, simulations, error mitigation, sensing, and dynamics, all kinds of supervised and unsupervised learning techniques. And this is an approach we have been taking, quantum reservoir, essentially to say it in one line, since I'm running out of time. So we have a collection of nodes. So originally, in a typical machine learning approach, all these nodes would have been some neural. This would have been a neural network, but here these are actually quantum systems, and many times quantum chaotic systems. So one exploits the nonlinearity of systems to be able to do better at learning these. Okay, now as I promised, does it help? Yes, it does help. At least on theory, there are enough results to show that there is exponential speed up to the algorithms, but there is a big but that needs to be written and followed up. There are many problems, but one problem that I will probably just say is that, first of all, we lack a fault-tolerant quantum computer as of today, without which many of these algorithms won't work. And also we lack what is called a QRAM, or a quantum random access memory. There are algorithms for it, but no implementation as yet. So those are the 2 important things, but then there is a whole lot of things. Each one can be a discussion and a longer talk in itself. Okay, I think I'll stop here by saying that quantum physics might be weird, but I think both quantum computing and quantum machine learning are more or less kind of here to stay. Thank you very much.
Yeah.
Yeah. So nice talk, sir. So in classical algorithms, like one computational complexity by number of basic operations. Like how do you compute that in quantum algorithms?
Yeah, it's the same. It's the number of applications of the unitary operators. So there are, if you look at a typical quantum algorithm, there will be all kinds of rotation gates, control NOT gates, and so on.
Yeah, is it okay to compare both of them? If it's that
see, in terms of number of operations, maybe yes.
Yeah.
It is simply like how many times you are applying an operator. At that level, it is okay. It is fair to compare. Yeah.
Okay. And like one more question is like, is it proven that these systems can be realized physically?
Yeah, so as I said, I had briefly said, so there are many experimental realizations which are out there, many of them, which are published and out there. So they are experimentally realizable. Yeah. And in fact, some of them have also been realized on the available quantum computers that are existing today. So the biggest one is about, I think, around 1000 qubits or so. And because of errors, its effective number of qubits is smaller. But within that, people have realized many of these algorithms. Almost all the algorithms have been realized in one form or the other in real experiments.
Thank you.
Yeah, good evening, sir. I actually had a very basic question. So what is the difference between the working of quantum computing and classical computing? Like, how is the principles of quantum mechanics and quantum physics, all of that we are learning right now, how is it applied to classical computing?
Okay, so in classical computing you work with bits like zeros and ones, but here you work with what is called qubits. There are state 0 and state 1, but the biggest difference comes from the fact that you can have almost infinite possible superpositions of this 0 and 1, which is not there classically. So that is the biggest difference. And when you have superpositions, all these operators in one go will act on the entire superposition together. So that is where all these speedups start coming up. Yeah.
Any other question? Anything from Zoom? No. Okay. Yeah, go on.
When you showed the pipeline data and the encoding and so on, so what came to my mind is that the read and write speeds of data from disk, right? If that remains slow,
yeah.
So is there work being done on that as well?
Yeah. So there are a whole lot of work being done on that, because all these speedups that I said, they don't count the time required to load the data, and that overhead somehow everyone assumes that can be done in linear time. And it's not clear that it is possible in linear time, but I think there are proposals to do that. Like QRAM is one of them. It's a promising proposal, but till now it has defied any experimental realization. It has not been realized in experiments. Yeah, so that's a challenge, and there is a whole lot of people working on that.
Good afternoon, sir.
Good afternoon.
So there are multiple, maybe 7 to 8 different physical quantum technologies. So are these quantum ML algorithms, are they agnostic of those underlying physical implementations?
Yeah, so these algorithms are agnostic to those different quantum technologies. But if you take an algorithm and you want to implement on a particular technology, then the actual details of how you will implement will depend on which one you are using, whether you are using superconducting qubit or a photonic processor and so on, because in each one the states are represented differently, and the operators are again represented differently. So at that level it will be different, but the algorithm will still be the same. Yeah.
So right now all this work of verifying quantum machine learning algorithms, they happen on the normal computers. Is that the way it is done?
So yeah, a lot of papers do use normal computers or simulators, but as I was telling for one of the earlier questions, there have been many experimental realizations. Either some are on existing quantum computers, and some are really an experiment done only to verify the algorithm. They can't work as a regular quantum computer. They are called quantum simulators. So those things exist. So it's just not fancy mathematics. So they do have real practical realizations. Yeah, that's been proven already. But the difference is that they are not at scale, not at a scale that industry would want.
Okay, if if there are no further questions, one from my side. This is a curiosity question. So, whatever you have been talking about is in terms of speeding up things. Are there classes of problems related to ML which classical ML algorithms will not even be able to solve, whereas you have some hope that quantum ML will be able to do it?
So there are classes of like learning hard distributions and so on, classes of problems like that, which are impossible for classical machines to solve. But there have already been work on showing that those hard distributions can be relatively easily learned by quantum machines, generative models. Yeah.
Okay. So it's also a qualitative job.
Yeah, that's right. Yeah.
Okay, so we will thank Professor Santhanam, and now we come to the open mic section. So what we'll do is, you heard all of us throughout the day, and now it's time to do the other way around. So you ask us your questions. Okay, just put your hand up, we'll send the mic to you. Ask us whatever questions you want. Obviously, if you ask us deeply technical questions, we may or may not be able to answer them. But questions related to use of AI in teaching, in research, or whatever else you think is important issue in your context, ask us, and there will be 3 people on the panel. The first, of course, met, well, Santhanam, I need you to go back there. Second person we have with us Professor Raghavendra Gadakkar. So many of you probably already know Professor Gadakkar. He is an evolutionary biologist from Indian Institute of Sciences, Indian Institute of Science, Bangalore. He is a National Science Chair at the Center for Ecological Studies, and more importantly, he is one of the topmost evolutionary biologists of the country. He is also extremely interested in AI, although he hasn't worked on it. But he has been visiting here, visiting us at IISER Pune for the last 1 week, and almost incessantly every day, AI is the main thing that we have been discussing in all kinds of combinations. So that's Professor Gadakkar. And the third person, you have been hearing a lot of me, but you'll probably have to bear me a little more, because I'm going to join both of them, and I'll be the third person. So this is not like a regular panel discussion where we discuss and then right at the end we open it for you. That's not what's going to happen. So here we are more or less going to stay silent unless you say something, and you can tell which one of us you want to answer the question, or if you do not have any choice, just let us know, and we will figure out who would like to answer the question. So anybody has anything, stick your hand up and somebody will give you a mic. Can we reduce this light a bit? It's a little too heavy. Right, yeah. Sure, you would like to start off?
Yeah, I know very little about AI, and whatever I know I've been learning from Sudhir. I just want to say that there are 2 things that interest me very much, which I think are problematic. If you remember today morning in Sudhir's talk, he said that if you are told not to use AI in your assignment, in your exam, then if you use it, you may get short-term gains, but in the long run, you suffer. The thing that interests me is how can we inspire people to capitalize on long-term and not short. So how can we inspire people to obey this rule, not by mandating it, but something that comes from them? That's something that I'm very interested in knowing. Can we actually inspire people not to do that? Similarly, the other thing that interests me is when we get something out of these models, how do we inspire people to verify it in various ways? In either of these cases, I don't think mandating works. So something has to be worked out at the psychological level where people feel that the most interesting thing to do is to verify. The most interesting thing to do is not to use it when I don't want it. The challenge of not using it when I'm not supposed to use it, and the challenge of verifying it, maybe even the thrill of showing it's wrong to verify. So these are the two things that interest me very much.
Santana, would you like to give some opening remarks?
Okay, so my interest in AI comes from background in physics. Often we look at models of physics, which are many of them, very useful in the physical context, as we say, for instance, you predict about something in spectroscopy, or something related to molecular structure, or something even related to what happens to the universe in the asymptotically and so on. But what is less appreciated is that all these many models of physics can also be used for computation as well as for machine learning purposes. In other words, every model that we know also can double up as a computational unit or a learning unit. So my interest in research or work with AI, or more correctly maybe machine learning, comes from such motivations. Yeah. And there are, I think, many questions related to ethical and other kinds of uses of AI. I'm following that, but I don't have great opinions on that to speak up right now.
Can somebody send the mic over there? Yeah.
Okay. So, is it possible to comment on the most promising quantum technology which you think is most promising? And if someone has to learn or has to make a career in quantum mechanics, then what kind of physics and mathematics background a person should have?
Okay, so the most promising, I mean, the one that might probably hit the market soon. If that is what you are hinting at, then I would say quantum communication, quantum cryptography, and quantum sensing. These are the ones which will hit the market soon in terms of reliable products. There are already products for quantum cryptography out in the market, and there are also products for quantum sensing. Things like sensing very small magnetic fields, stray electric fields. They are useful even for, let's say, detecting bombs from, let's say, a few meters away and so on. So those kind of things already exist in the market, and they are under continuous improvement. Even though much of the limelight is taken by quantum computer, I think a fault-tolerant quantum computer is still some time away. It is going to take some time, maybe 5 to 10 years, or maybe even more. And about the next part of your question on what you probably, you asked about what should be.
Yeah, so actually thanks for answering this, but the question was little different. Though whatever you said is very helpful. The question was really like at the physics level, like maybe if it's the superconductor, or whether it's the, the photonic level, or all those technologies which are emerging. And for that, what kind of physics and mathematics background a student should have is the question.
Okay, so I think the usual mathematics and physics taught in all the bachelor's and master's level. That is the kind of physics needed. But I think a lot of quantum computer is not about quantum also. You need electronics engineers, you need electrical engineers, and many others as well. So while the core aspects will need quantum physics, mathematics, linear algebra, for instance, and differential equations, but getting things to work requires like RF engineers and control systems and all kinds of things. Even things like software engineers who can write codes that will translate from what you write and tell the machine to do what it needs to do and so on. So there is a whole lot of things which are not quite core quantum but are required to get something up and running.
Hello, sir. My question is related to Honorable Pranay Goyal, sir. What he mentioned about digibone. So it's a general question. I think you may answer. So the question is, have you thought anything about pitching that in front of the Honorable Central Government of India under the Ministry of Health? Because digibone and a couple of postdocs he has done in USA, he came back to India and now he's, I think, a physical asset. So the central government can set up campaigns and run schemes and set ambitious targets rather, just like we eradicated TB. Okay, so to create India an arthritis free country or anything like that, it would be helpful. And my suggestion and actually a request is to pitch this in front of the central government of India and take this to local level in rural population where arthritis is a major issue and the local communities aren't able to defend it. Thank you.
So I obviously cannot speak on his behalf, but since I know Pranay extremely well and I have spoken to him many times about this, he obviously has these kind of things in mind, which is why he has made everything open source, which is why he has put up everything on GitHub, so that people can take this and build their own applications. And also remember, a lot of our funding is coming from the central government, right? So obviously all these reports, etc., these do go to the central government and they are reasonably well aware of the kind of work that we sitting here at a central government institute are doing. So I'm absolutely confident that Pranay is already working strongly on this. Thank you. Huh.
So my question is regard to application of AI in ecology and evolutionary sciences. So generally, like in the sort of classical experimentation sense, how do you see that integrating AI in our current framework can lead to innovate our experimentation and lead to somewhere that earlier used to be difficult, or basically the questions that could not be tested earlier but could now be. So how do you see, where do you see this going forward?
I mean, all kinds of things are already happening. So, for example, there is a lot of AI slash machine learning algorithms which are being developed for bioacoustics kind of studies. So, record the songs from different places. A lot of citizen scientists, they record bird calls or let's say insect calls, but then identifying them becomes very difficult. So, people are trying to come up with AI ML things for that. Similarly, if you look at long-term monitoring data of population, of vegetation, of many other things, terabytes after terabytes of data, and very often scoring them becomes a massive challenge. People are trying to develop, I shouldn't say trying, they have already developed models with different levels of success for identifying those things. These obviously also have conservation related applications. Then, so I would like to say that a lot of stuff which earlier was very manual and tedious and error prone is now people are trying to develop AI ML related things to get those things done. They will obviously now become automatic. They will obviously now become less tedious. One has to see how much, what happens to the error part of it. That is where a lot of the work is going on. So that is the direct, application over here. Professor Gadekar has something else in his mind.
Just wanted to give one more example. A very ambitious program is being thought of, perhaps already started implementing, and it sounded absurd. It would sound absurd without AI. but with AI it doesn't sound so absurd. And that is to take samples of soil, water, air, and simply sequence everything there without worrying about where it comes from. And then find ways of then binning those sequences into different species. So what we normally do is we take a species, we identify it, we show it a taxon, we are sure this is Rhopalidium, then we say we'll sequence its genome. The idea now is just to sequence all DNA which is present in the environment and then see whether you can post facto find out how many species are there, what is the diversity. So basically sequence the entire Earth's biodiversity, first sequence, then classify. This would have sounded absurd in the absence of AI, but doesn't look so absurd now.
And this is an absolutely fundamental question because, as you know, we still don't know simply how many species are there, pretty much for any group. And the groups that we really don't know are the microbes. Okay, so a lot of microbial diversity will get, hopefully uncovered by, doing what Professor Gadakkar is saying. And as he rightly pointed out, no chance if you don't have high quality AI ML algorithms. Yeah. Go on, something over there.
So there is a question on Zoom webinar.
Yeah, go on, please. Let's give the Zoom guys a chance.
Yeah. So they are curious about the opinions of the panelists on how often technologies that are perhaps related but not the same are conflated under AI. For example, ML is useful for processing data, while LLMs are more often used for ideation. Are these various aspects / categories not separate enough to warrant distinct and dedicated discussion?
Absolutely correct. They are very, very separate. So AI is an umbrella term, ML is an umbrella term, and within AI, LLM is just one thing. The moment you put agents on top of that, agentic AI, things go in very, very different direction. So in any proper computer science conference, if you go there, people are not going to talk about AI ML in the loose way that we have been talking about here. They will talk about the specific thing that is being talked about. But since in the context of this conference, we were generally addressing people who are not into AI ML and we're just trying to get an overview of what is happening, that's why we have been using the terms very, very loosely. But people who are in the field, they will never use it that loosely. They'll be much more specific about it. So absolutely correct, and that's how people normally do it. Am I right, Santana? Yeah, I do. Yeah.
And there is another question by Nishchay Jajodia, who is asking, what challenges does quantum computing pose to existing cryptographic systems, and how can security and confidentiality be maintained in the quantum era?
So this, okay, so there is quite a bit of security threat in the future, in the sense that if and when a full-fledged fault-tolerant quantum computer becomes available, then it would be possible to break these crypto systems, which means that everything from our passwords to whatever we transact on the internet can easily be kind of decoded. But that is a bit far in the future. But what's happening is that currently there are many agencies and many others who are doing what is called like harvest now, decrypt later, meaning that even though you can't decrypt now, just collect the messages now, keep it somewhere, so that maybe 20 years later or whenever it becomes possible, then you can decrypt and see what is actually there. So that is one kind of danger which is currently also happening. And one way to break out of this is what is called this post-quantum cryptography techniques. So these are what are called quantum resistant algorithms. They are not exactly quantum algorithms, but are the usual classical mathematical algorithms. And they are in some sense quantum resistance. So including them, enabling these security with this PQC, post-quantum algorithms, will have the effect of securing against these kind of attacks, which is happening now.
Okay, yeah. Go on, please. Somebody over here. Okay, go on.
So, what practical AI skills a researcher to learn today to stay relevant in future research?
That's not one thing which says, learn programming and you are done. It's a bunch of things. So, for example, as Professor Nagarjuna pointed out, one major thing is prompt engineering. You really need to know how to talk to the AI, the LLMs. Another massive thing is that there are all kinds of platforms available which are specialized for specific tasks. So, for example, for searching, let's say literature search, or for certain kinds of reviewing, or many other such stuffs. So you also need to have a good idea about what is the best platform that is available for those tasks, and at the same time it will actually be a good idea to have a basic ability to do coding using LLMs, such that if you have an idea in your head, I'm not talking about making an app and sell it for a few crores, no, not that. For your own scientific stuff, if you want to, let's say, parse the data in a certain way, or if you want to ask a question, and if you want to bring two, three, four things together in a particular way for doing an analysis, instead of going and paying a software designer for it, you should be able to do it on your own. So at a very rough 101 level, these are the things that one can talk about right now, and of course a little bit understanding of agentic AI and how that works. Please appreciate one thing, that this is a field which is evolving at a breakneck speed. Okay, every few weeks new things are coming up, new models, new technologies, new platforms, blah blah blah. So my feeling is that if as a student you are thinking about this question, a, figure out what is the situation right now, and b, keep an eye on how things are evolving, because it doesn't look like that the pace of evolution will slow down very soon. so so please keep an eye open, and as and when things come, you need to be flexible and adaptable. And above everything, it's a slightly different way of thinking about the scientific process. Okay, so you also need to adopt that way of thinking about how to do science. Okay, so roughly speaking, these are the 3 4 things that I can talk about. Thank you. Somebody over there.
Good evening.
Good evening. Yeah.
Yeah, so in all the talks that we heard today, there was one common pattern. The scientific community, the researcher provides data and the data to the AI machine, and the machine analyzes it and provides some output. So, but the prompt for thinking, I think Professor Nagarjuna also said this, prompt engineering. So the prompt for the AI is not thinking on its own. The AI analyzes millions and billions of data and produces output. So in the future, are we looking at a state where AI does this, provides the prompt to itself on its own? So basically, it starts thinking.
That is already there. So there are papers from, for example, check out Sakana AI. Okay, these are end-to-end things. A simple prompt has been given right at the beginning. The AI has thought about the prompt. The AI has designed the hypothesis. The AI has designed the numerical experiments needed to do the hypothesis. The AI has written the code. The AI has run the thing, the programs. The AI has got the results. The AI has analyzed and interpreted the results, and the AI has written the paper, which has been submitted to computer science, prestigious computer science, conferences in an anonymous way, and has been accepted. And Sakana is just the first set of people who did that. There are other things like that that are happening. There is something known as AI archive, where papers that are entirely written by AI are being put up. So yeah, you don't even need to go to the future. It's already happening. The future is here. Yeah, somebody at the back. Okay, well, just one second. There's somebody over here who has been holding on for a long time. Yeah, you go on and then we'll go to you. Okay? Bolo.
So my question is about environmental and social impact of AI. So like I'm reading that a lot of companies and like even Indian government, they are like planning to spend like billions of dollars on AI infrastructure and training. But currently these data centers like consume a lot of energy and water. So like as scientists who actively work with AI, so like I'm interested in knowing your thoughts, and do you think it is really sustainable for long term, or uh, do you think like we need to modify, or the output of AI, is it worth the environmental or like the social cost that it is taking?
Uh, can I take that one? Yeah, okay. So, have you heard of something called ENIAC? Okay. So, when the first computer was built, it was a massive thing. Okay. Filled up one big, huge room. Okay. And obviously, people were worried about similar questions, right? But then what happened was, as time went by, the technology changed. We went from valves, which was how the first ENIAC was built, we went to semiconductor chips. The moment that happened, the entire thing became smaller, the entire thing became much, much more energy efficient. Yet, when, for example, I was at your age, a proper computer had a huge box and a huge monitor, etc., etc. And now it has become, your smartphone. Your smartphone actually is a computer and is way more powerful than the computer that sent the spaceship to the moon. So attendant technological innovations in other fields, in this particular case electronics, often drives down the cost. What I have a feeling is something like that is very likely to happen in the context of AI. As a matter of fact, it has already started happening in certain areas. So for example, if you remember Professor Bidarth talking in the morning, he said that we are using a 276 million model. Okay, 276 million parameter model, which is a very, very small model, which can probably run, if you have a slightly powerful smartphone. So people are extremely mindful of this problem, and all kinds of things are happening. All kinds of technological innovations are happening to bring down the cost of training, to bring down the cost of running the model, and so on and so forth. So to answer your question, if we keep on guzzling, I mean, if the LLMs keep on guzzling the same amount of electricity and water, etc., and there are no innovations, then will it be sustainable? I don't know. Very unlikely, because the cost is really, really high. But at the same time, are there indications that things are going to improve? I would like to say yes. I can see both structural innovations happening, and I can also easily foresee innovations happening in terms of the infrastructure itself. So I think it's a little too early for me to give a definitive answer to this question, but definitely things are looking pretty positive as of this moment. I'm not pessimist. Okay, thank you. Somebody else at the back. Yeah.
Hello, sir.
Hello.
This has been a illuminating session. So I have a few questions to ask. Firstly, in your talk, you mentioned that we can use AI to nudge us in the right direction for learning. So can you elaborate on that with a few examples?
Yeah, sure. So there are very nice assistants available both on ChatGPT as well as Gemini, where if you ask it a question, it is not going to give you a direct answer. It is going to kind of ask you, okay, what do you think about it? It will force you to say something. And then it will say, okay, you are thinking about it like this. Okay, maybe, have you thought about that part? Or how do you define this part? Or, are you sure about that part? And so on. So instead of giving you a direct answer, it actually slowly guides you towards the right answer. So that is what I had in mind when I said that, there are possibilities, and these are all already existing in the free versions. You can, play with those things yourself. So that's what I meant by saying, guided learning can sometimes be useful. To take it one step further, this is something that, some universities in the US, they have done it. They have essentially taken all the material from a professor's course, their video lectures, class notes, etc., etc. They have digested it in AI, and they have essentially created a teaching assistant. So now, instead of going to a physical teaching assistant, you can actually go to this AI and then ask the question in the context of what has been taught in the class, as opposed to the general knowledge available on the internet. So, I mean, I haven't played with those systems myself, so I can't really say about how good or bad they are. But from what I've been reading about them, looks like they are doing, pretty well. Those kinds of systems are also available. So that's the other kind of thing that I had in mind when I said that statement. Okay.
Another question to Santanam sir. As a biology student, if I want to enter into quantum mechanics, if I want to start learning about them, how would you approach or how would you recommend I start?
Take his course. As simple as.
So I don't know, it's a bit of a hard question, but I think familiarity with some amount of linear algebra will help, even if not quantum physics. At least linear algebra is necessary to work with quantum computing algorithms or even understand quantum computers and things like that. So there are specialized books on quantum computing for example, engineers. There's a book called Quantum Computing for Engineers. Till now, I have not seen quantum computing for biologists. Though there's one I have seen, quantum computer for babies. Which I think
babies, but not biologists.
Not biologists.
Right. Fair enough.
Yeah, so it doesn't exist, but I think it's someone needs to think about it, and maybe a biologist should write such a book after understanding it. So I think they would have the perspective of how to address it to another biologist.
Yeah, Professor Nagarjuna. Yeah, Professor Nagarjuna here, first row.
Question which was previously asked and answered by Sutit, but I wanted to ask Santanam about the prospect and possibilities of reservoir computing and cutting down the energy usages, because I hear from many of the papers that I read, there seems to be some amount of hope there. So I wanted to get your reaction on that.
Yeah, so the attractive part of this reservoir computing is the number of parameters that are required to train is drastically smaller than a typical deep neural network. So which means that it will translate in terms of far lesser energy consumption and so on. But I am still kind of baffled by the fact that why industry has not adopted it in big scale. So there have been, if you see papers, there are all kinds of demonstrations of learning tasks using reservoir approach. But somehow I am yet to see any industrial scale application. And it's not even that, I'm just talking of the usual reservoir computing, not the quantum reservoir computing, where I think we have all the computing elements, everything which can be done for an industry at scale. So that is something that baffles me yet. Maybe just someone needs to do it, I think.
Yeah. Okay, there are quite a few more. Maybe somebody from this side, we haven't taken any question from this side.
Good evening, sir.
Good evening.
Sir, I do my PhD in novel gene identification and its characterization via metagenomic pathway. So I have two questions. How would I can approach using AI not just to fill missing sequence in phylogenetic tree, but to intelligently explore the ancestral function landscape that nature has not preserved? And one philosophical question is like as we define novel gene, so what is means how do you as an evolutionary biologist define evolutionary novelty at the molecular level?
Evolutionary novelty at the molecular level?
Yes, sir. like we said we identified a novel gene, but like we having AI tools, and it can predict and it can extend. So how can we say we have find a novel at the molecular level? How can you say novelty at the molecular level when evolutionary it is not exist? So
See, novelty at the molecular level means what? A sequence which didn't exist, or a sequence which you have not found in another context, now you can find it. But I think what you really mean is functional novelty, right?
yes, sir.
But the point is, structure function correlations are still not well understood. Even with AlphaGo, where you can go from the sequence to the structure,
Yes, sir.
you still cannot do very well going from structure to function. Am I right on that, Professor Kadekar? Yeah, so structure to function is something that you cannot do even in the absence of AI. So AI, it's not entirely clear, at least based on where the state of the art right now is, that AI is going to help you in going from structure to function. Okay, so that's not happening, or at least that's not happening as of this moment. It might happen tomorrow. As of this moment, it's not happening. What was the first part?
Sir, the first part is when we like metagenomically we do and sequence the complete genomes, and we find or find some hits and gene. So we'll do phylogenetic analysis and we search for homology. So how can I use AI to accurately find the gene and predict that their function would be there as a novel variant?
See, again, if you are talking about going from structure to function,
Yes.
I already answered that question.
Yes.
It cannot be done. Now, if you are asking me how to use machine learning methods to make better phylogenetic trees, I personally don't work in that field. Therefore, I can't give you an answer saying, hey, this is the algorithm that you need to use. Okay. But a lot of work is happening along that axis. And one just needs to figure it out. Maybe ask ChatGPT. Yeah, but honestly speaking, there is a lot of work happening over there. So you just need to look it out. It's a factual piece of information. I personally don't have it because I don't work on that.
Thank you, sir.
Thank you. Yeah.
Good evening, sir.
Yeah.
My question is, science self not studying about chemistry, physics. Science is asking a question. Then how AI helps supports to the early researchers or student to ask a better question, not giving a faster answer.
Okay, would like to take that? How AI will help someone to ask a better question? Okay. To the early researcher. Have you read Douglas Adams' Hitchhiker's Guide to Galaxy? Are you aware of this book?
Sorry, sir, I don't know.
Fine, doesn't matter. So in that book, a computer is asked a question about, what is the answer to the ultimate question? And it gives an answer. And the answer makes no sense. Then they say that, okay, we don't understand how this is the answer to the question. And then the computer says that, look, figuring out what is the correct question is a much more difficult thing than figuring out the answer. Okay. And although that was said in jest in that particular book, but in reality, very often that is the situation. So figuring out what is a good question, what is a nice question, actually is something that very often the beginner is not even able to do. They might stumble upon a good question by accident. That's a different ball game. But algorithmically, or using their experience to figure out what a good question is, answering which is going to lead to a substantial leap in the field as opposed to an incremental change, that is not a beginner's job to begin with. So you can at your level simply say something like, hey, ChatGPT, give me 5 great unanswered questions on this topic. Okay, and ChatGPT will give you 5 different things. Whether any of those questions are really good or not, that judgment, that comes from a very senior researcher. Professor Kandekar?
This is one area in which we might still be superior to AI.
As of this moment at least. Again, I don't know what will happen tomorrow. So yeah, so the problem statement that you have given is not a problem statement for an early researcher. That's the problem statement of somebody who has spent a lot of time in the field, understands the field, and therefore can have their own judgment on what is a good question and what is not. Okay. Okay. Yeah, people, we need to end at some point. So this will be the last question that we will take. And after that, some of us are going to be available there. So come back to us. So yeah, somebody from over there. Actually, you've already taken the mic.
Sir, I have a question related to physics and mathematics training. So what generally what I believe what happened to the previous generation of mathematicians and physicists was that they had some problems to ponder over. So they banged their head against the wall for quite some time. And when they couldn't do that, they asked their professors or whatever they did. So what changes for our generation of people? I mean, what is the ideal procedure for learning that we should follow to get the best out of AI?
You want to take that? Okay. So this is pretty much what I was trying to allude in the last slide of my thing. Okay. Which is that if you give your, if you substitute your brain with AI, then obviously you won't have a brain. Therefore, instead of avoiding the friction of learning, I will recommend that you embrace the friction of learning, which basically means that when you are faced with a problem, don't just go and ask ChatGPT for the solution. Just, hammer on it. Spend as much time as you can on it. Spend till that point when, looking at that problem just wants you to just go away. Spend that much of time. And then when you have an answer, or maybe you have 3, 4, 5 different answers, and you have already made some judgment about, I think this is my first priority answer, I think this is my second priority answer, and so on, that is when you go to AI. Because normally, think about it, if you don't have AI, what will you do? That is the point when you will go to your friend, or that is the point when you will go to your teacher and say, hey, this is the amount of thinking that I have done. Now tell me, what can I do better? Or, just give me your opinion on these thoughts. Use AI in that context. If you do it that way, see, even when you go to a human being, let's say a friend or a teacher, do you think every single opinion that they will give you is going to be right? No. Sometimes they do make mistakes, right? Teachers always make mistakes. But because you have thought through the whole thing, therefore when you get a wrong answer, you will be able to say, hey, this answer cannot be correct. So thank you for your time, but I think what you are saying is wrong. That is the state where you are going to become an expert. You've started on the path of becoming an expert. And use AI exactly in that way, rather than going to them with the problem and saying, hey, give me 5 solutions to this. And then I have no idea which one is right, which one is wrong, which one is good, which one is bad. And I will take, whatever I think, eeny, meeny, mo, this is the one. Don't do that. I think if you just follow this one advice and forget about everything else, mostly things will work out.
Okay. Yes, sir. Thank you.
Okay. Thank you very much, people. And we are coming towards the end of this session. I will now invite our director, Professor Sunil Bhagwat, to come and say a few words. Yeah, prior to that, we go down. It's just going to be a few words now.
Good evening. After listening to an entire day of what AI can do, I'm sure there have been people who have generated a lot of enthusiasm on one hand, and possibly some people who have turned pessimistic and think that there is no point in learning anything further and that AI can do all of it. But what I would like to say is that towards the end, what Professor Gadekar said, that we have to, and in fact that becomes a nightmare for an institution head, that if my students are going to think that AI can do it, why should I? Then the employers will think that if AI can do it, why should I recruit these students? And which means the students have to always make sure that they are one step ahead of whatever alternative can do. I will also take you back to historic or prehistoric times when education and knowledge simply meant memorizing things. And then came the books. When books came, everybody thought that now learning and teaching process is no longer required because all the knowledge is available in books. We know now that it's far from true. The same thing happened maybe 15, 20 years ago when Google started throwing answers for anything and everything. And now we know that all those answers are not necessarily the real ones. And we understanding what is good, what is not good is still required. So I'm hopeful that the brains of this generation will continue to find ways of being superior to AI and still stay relevant. There are, of course, things we need to take precautions with. For example, what data we provide, and if it is a limited form of data, then naturally it will build in biases. If we are not careful about data, it will lead to data leakage and privacy issues. If we are not careful about what the answers are given and we directly try to use them, we will lose the human touch, the human values. But used correctly, it will be a huge productivity tool, and it doesn't always have to mean that people will get de-skilled and therefore lose relevance. So staying a step ahead, mankind has been able to do through history, and I am hopeful the same will continue to be the case. Throughout the day, I'm sure our speakers have generated questions in you, and that means it was successful. And asking the right kind of questions is something, even as a teacher in a classroom, I would rather judge a student on the basis of a question he or she asks instead of the answer he or she gives to a question I pose. So generating questions is definitely the way of making sure that you are ahead of it. And wish you all the best doing that. Thank you.
Thank you very much, Professor Bhagwat. He unfortunately had a meeting in the morning, which is why he could not be with us throughout the day. So with this, we come to the end of today's program, AI at IISER Pune. Thank you very much. Thanks to our two sponsors, Informatics Publishing and A3 Capital. So Devesh Thakur from Informatics Publishing and Sanjay Farke from A3 Capital. Both were very, very enthusiastic about the project, and both of them supported us. Our speakers, 9 of them. Last moment, I approached them and said, "Hey, come over, give a talk," and none of them said no. Thanks to all of you, and special thanks to all of you who came here today. I know there is an election happening today. I know there is a strike happening today. In spite of that, all of you turned up. Thank you very much. Special thanks to Science Media Center for their superb support. Special thanks to our IT department and all the other departments of IISER Pune who came together to make this event happen. And people on YouTube, people on Zoom, many of you asked questions which unfortunately due to the want of time we could not take up. So really sorry about that, but thanks for joining. Thanks for coming, people. And a huge round of thanks for all our about 14 volunteers, both BSMS and PhD students of IISER Pune who made this entire thing happen. Thank you very much, people. Good day.
Stayed back to just say one thing. Huge thank you to Sutirth for taking lead in organizing this.